We have explored less than 5% of the universe we live in. The rest remains hidden behind a horizon we can never cross, a boundary drawn not by technology or time, but by the speed of light itself. And yet, within that thin slice of cosmos we can observe, stretching 93 billion light-years from edge to edge, we have found things that should not exist. Storms raging with 1,000 times the fury of anything on Earth. Black holes so massive they warp spacetime into shapes our equations struggle to describe. 2 trillion galaxies scattered across the void, each one a city of billions of stars, and we have barely begun to catalogue them. We thought we understood how planets form, how stars die, how galaxies evolve. Then we looked closer. We found lightning on Jupiter that tears through clouds with 10,000 times the power of a terrestrial bolt. We discovered neutron stars so dense a spoonful would outweigh a mountain. We detected planets orbiting distant suns in configurations that make no sense according to the rules we wrote. And beneath it all, holding the entire cosmic architecture together, we found something we cannot see, cannot touch, cannot explain. 95% of the universe is made of substances we have never identified. Dark matter, dark energy. Forces so fundamental they shape every galaxy, every star, every atom, and we do not know what they are. This is not a story about what we have learned. This is a story about how much we have left to learn, about the mysteries hiding in plain sight, the questions we have not yet learned to ask, and the humbling realization that everything we call reality might be a single thread in a tapestry far stranger than we ever imagined. For the next 4 hours, we're going to the edge of everything we know, and then we're going to look beyond it. Welcome to Space Dust. If you're new here, please subscribe. We make these documentaries every day, and we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in for a great journey. 4.5 billion years ago there was no Earth. There was no Mars, no Jupiter, no Saturn. There was no sun burning at the centre of a stable arrangement of planets. There was only a cloud, a vast, cold, diffuse cloud of gas and dust drifting through space. Hydrogen mostly, with traces of helium and frozen particles of heavier elements forged inside stars that had lived and died long before our story begins. This cloud had no name. It had no purpose. It was simply there, suspended in the void, stretching across several light years, doing nothing in particular. And then something disturbed it. Maybe it was the shockwave from a nearby supernova. Maybe it was the gravitational nudge of a passing star. Whatever it was, it caused a ripple, and that ripple caused the cloud to do something it had never done before. It began to collapse, slowly at first, then faster. Gravity pulled the particles inward. As they fell toward the centre, they picked up speed. As they picked up speed, they collided. As they collided, they heated up. The cloud began to spin, flattening into a disk the way pizza dough flattens when you throw it in the air. At the centre of that disk, pressure and temperature climbed. Atoms smashed together. The core got hotter, and roughly 50 million years after the collapse began, something ignited. Hydrogen nuclei fused into helium. Light erupted. The sun turned on. That moment, the ignition of our star, marks the beginning of the solar system as we recognise it. But the story was far from settled. Around the newborn sun, a spinning disk of leftover material remained. Gas, dust, ice, rock. All of it orbiting in the same direction, all of it governed by the same physics. Particles stuck together. Pebbles became boulders. Boulders became planetesimals. Planetesimals smashed into each other, sometimes merging, sometimes shattering. The early solar system was not a calm nursery. It was a demolition derby. Collisions happened constantly. Bodies grew and shrank and grew again. Some objects accumulated enough mass to start pulling in everything nearby. These became planets. Others never got the chance. They remain today as asteroids, comets, dwarf planets, the leftovers that never made it to the main event. The architecture we see now, the neat arrangement of rocky planets close to the sun and gas giants farther out, was not the original design. Jupiter and Saturn may have migrated inward, then outward again, their gravity scattering smaller bodies across the solar system. Neptune and Uranus may have switched places. The entire structure we think of as stable has been shaped by billions of years of gravitational chess, with planets pushing and pulling on each other, nudging orbits, flinging debris into the outer dark. We live in the aftermath of chaos. The solar system looks calm because the worst of the violence is over, but the scars remain. Take Jupiter, the largest planet in the solar system by a margin that makes comparisons almost meaningless. If Jupiter were hollow, you could fit roughly 1,000 Earths inside it. 1,000. It is not quite large enough to ignite fusion and become a star, but it dominates everything around it. Its gravity shapes the orbits of asteroids. It herds comets. It has pulled in or flung away countless objects that might otherwise have wandered into the inner solar system and collided with Earth. In a very real sense, Jupiter is a shield. It is also a laboratory for atmospheric physics that we are only beginning to understand. The most famous feature on Jupiter is the Great Red Spot, a storm large enough to swallow the entire Earth. Astronomers have been watching it since at least the 1600s. For centuries it was assumed to be a relatively shallow weather system, a swirling patch of high pressure sitting on top of deeper, calmer layers. Then NASA's Juno spacecraft arrived. Juno carries instruments capable of peering beneath the cloud tops, measuring the structure of Jupiter's atmosphere in 3 dimensions. What it found was unsettling. The Great Red Spot is not shallow. It extends downward more than 50 times deeper than the initial models predicted. It is not a surface storm. It is a column of churning gas reaching hundreds of kilometers down into the planet's interior. The energy required to sustain something like that for hundreds of years is staggering. We still do not fully understand where that energy comes from, or why the storm has not dissipated. And then there is the lightning. Earth has lightning. Everyone knows what lightning looks like. A bright flash, a crack of thunder, maybe a few 100 million volts. Impressive by human standards, unremarkable by Jupiter's. Recent observations from Juno suggest that individual lightning strikes on Jupiter can be 500 to 10,000 times more powerful than the strongest bolts on Earth. Some analyses, depending on how you measure the energy release, suggest the upper range could be even higher. These are not occasional anomalies. Jupiter experiences lightning constantly. Flashes erupt across its cloud bands in wavelengths our eyes cannot see, releasing energy that would vaporize anything nearby. The atmosphere is not just turbulent, it is electrically violent in ways that make Earth's most intense thunderstorms look like static shocks. Why is Jupiter's lightning so extreme? The leading theory points to convection. Jupiter has no solid surface. It is a ball of gas all the way down until the pressure becomes so intense that hydrogen starts behaving like a liquid metal. Heat from the deep interior rises, cooler gas sinks. This convection churns the atmosphere at scales and speeds we cannot replicate in any laboratory on Earth. As gas parcels rise and fall, they carry water droplets and ice crystals with them. These particles collide, generating static charge the way rubbing a balloon against your hair does. Except on Jupiter, the scale is planetary. The charge builds until it arcs across hundreds of kilometers in a single discharge. The result is lightning that could power a city for weeks. Move outward, and you reach Saturn. Smaller than Jupiter, but still massive enough to hold more than 700 Earths. Saturn is famous for one thing above all else: its rings. The largest, most spectacular ring system in the solar system. From a distance, they look solid, like a smooth disk of material circling the planet. Up close, they dissolve into billions of individual chunks of water ice, ranging in size from grains of sand to house-sized boulders, all orbiting Saturn in narrow bands. The rings are thin. If you built a scale model where Saturn was the size of a basketball, the rings would be thinner than a sheet of paper. And yet they stretch outward for hundreds of thousands of kilometers. We do not know how old the rings are. Some models suggest they formed recently, perhaps only a few 100 million years ago, when a moon wandered too close to Saturn and was torn apart by tidal forces. Other models argue the rings are ancient, dating back to the formation of the solar system itself. The truth is, we are still guessing. What we do know is that the rings are not stable. They are slowly spiraling inward, raining down onto Saturn's upper atmosphere. In a few 100 million years, they may be gone entirely. We are living in a narrow window of cosmic time when Saturn happens to have rings. 1 billion years ago, it might have looked different. 1 billion years from now, it almost certainly will. Beyond Saturn lie Uranus and Neptune, the ice giants. Both are smaller than Jupiter and Saturn, but still massive by any reasonable standard. Both have atmospheres of hydrogen and helium mixed with water, methane and ammonia ices. Both have narrow rings made of dark material, nothing like Saturn's bright bands. And both are spectacularly cold and distant. Uranus orbits the Sun at roughly 19 times the distance Earth does. Neptune sits even farther out, 30 times Earth's distance from the Sun. At that range, sunlight is faint. The energy-driving weather comes mostly from the planet's interiors, and yet both worlds have some of the most violent atmospheric conditions in the solar system. Neptune holds the record for the fastest winds ever measured on any planet. Storms race across its surface at speeds exceeding 2,000 km per hour. For comparison, the most intense hurricanes on Earth top out around 300 km per hour. Neptune's winds are 7 times stronger, driven by mechanisms we do not fully understand. Uranus, meanwhile, is tipped on its side. Its rotational axis is tilted more than 90 degrees, meaning its poles point roughly where most planets' equators do. One theory suggests Uranus was knocked over by a massive collision early in its history. Another proposes that gravitational interactions with migrating planets during the solar system's chaotic youth gradually tilted it over time. Either way, the result is a planet where each pole experiences 42 years of continuous sunlight followed by 42 years of darkness. The seasonal effects on its atmosphere are extreme and poorly understood. The planets are strange, but the moons are stranger. Europa, one of Jupiter's 4 largest moons, is slightly smaller than Earth's moon. Its surface is a shell of water ice, smooth and bright, crisscrossed with reddish-brown streaks and cracks that stretch for thousands of kilometers. That surface is cold, around negative 160 degrees Celsius. It looks dead. It is not. Beneath the ice, there is an ocean. A global ocean of liquid water, likely containing more water than all of Earth's oceans combined, sealed under a crust that could be anywhere from 10 to 30 kilometers thick. We have suspected this since the late 1990s, when NASA's Galileo spacecraft measured disruptions in Jupiter's magnetic field near Europa. Those disruptions could only be explained by a vast body of electrically conductive liquid beneath the surface, salt water. The energy keeping that ocean liquid comes from tidal heating. Europa's orbit around Jupiter is slightly elliptical, nudged into that shape by gravitational interactions with the other large moons. As Europa moves closer to and farther from Jupiter during each orbit, the planet's immense gravity squeezes and stretches the moon's interior. That flexing generates heat, enough to keep an ocean liquid for billions of years beneath kilometers of ice. Where there is liquid water, where there is energy, where there is time, the question of life becomes unavoidable. Europa is one of the most promising places in the solar system to search for biology beyond Earth. Then there is Enceladus, a tiny moon of Saturn barely 500 kilometers across. For a long time, it was thought to be geologically dead, just another frozen lump in Saturn's crowded system. Then in 2005, the Cassini spacecraft flew past and saw something no one expected: geysers. Enormous plumes of water vapor erupting from cracks near Enceladus's south pole, shooting hundreds of kilometers into space. Cassini flew through those plumes and tasted them. Water, salt, organic molecules. The geysers are fed by a subsurface ocean, heated by the same kind of tidal flexing that keeps Europa's ocean liquid. The ice crystals from those eruptions do not fall back to the surface. They escape into orbit around Saturn, forming a faint ring called the E-ring. Enceladus is actively feeding one of Saturn's rings with its own ocean water. It is one of the most geologically active bodies in the solar system, and it is smaller than some asteroids. Titan, Saturn's largest moon, is in a category of its own. It is bigger than the planet Mercury. It has a thick atmosphere, denser than Earth's, made mostly of nitrogen with traces of methane. That methane plays the role on Titan that water plays on Earth. It rains methane. It forms methane rivers and methane lakes and methane seas. The largest of those seas, Kraken Mare, is bigger than the Caspian Sea on Earth. The surface temperature on Titan hovers around negative 180 degrees Celsius. At that temperature, water ice is as hard as the rock. Methane is liquid. Titan has weather. It has seasons. It has a hydrological cycle, just not one made of water. When the Huygens probe landed on Titan in 2005, it sent back images of a landscape that looked hauntingly familiar. Rounded pebbles, drainage channels, a flat plain that might have been the bed of a dried-up lake. Except the pebbles were made of ice, and the liquid that carved the channels was methane. Titan is Earth with the temperature dial turned all the way down and the chemistry flipped upside down. Beyond the orbit of Neptune lies a region called the Kuiper Belt, a vast ring of icy bodies and dwarf planets stretching from roughly 30 to 50 times Earth's distance from the Sun. Pluto lives here, along with thousands of other objects, some nearly as large. The Kuiper Belt is what is left over from the planet-building era. The material out here never accumulated into a full-size planet, likely because Neptune's gravity kept stirring things up, preventing the slow, steady collisions that build worlds. Instead, the Kuiper Belt remains a frozen reservoir of primordial material, a snapshot of the early solar system preserved in deep cold. It is also the source of short-period comets, those icy visitors that swing through the inner solar system on orbits, measured in decades rather than centuries. And then there is the Oort cloud. We need to be clear about something. No one has ever seen the Oort cloud, not directly. It has never been photographed. No spacecraft has reached it. No telescope has resolved a single object confirmed to belong to it, and yet astronomers are nearly certain it exists. The Oort cloud is predicted based on mathematics and on the behaviour of comets. Long-period comets, the ones that take thousands or even millions of years to complete a single orbit around the Sun, come from every direction. Not just from the plane where the planets orbit, but from above and below, from all angles. That distribution suggests they are coming from a spherical shell surrounding the entire solar system, not from a flat disk like the Kuiper Belt. The Oort cloud is thought to extend from roughly 5,000 astronomical units to as far as 100,000 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. 100,000 astronomical units is nearly 2 light years. That is halfway to the nearest star. The Oort cloud, if it exists the way models predict, is not a solid structure. It is a diffuse collection of trillions of icy bodies, each one drifting in near total darkness, barely held by the Sun's gravity. Most of them will orbit out there forever, undisturbed. Occasionally, one gets nudged by the gravity of a passing star or a random gravitational fluctuation. Its orbit shifts. It begins to fall inward, accelerating as it approaches the Sun. By the time it reaches the inner solar system, it is glowing, a tail of gas and dust streaming behind it. We call it a comet. Every long-period comet we have ever observed is thought to have come from the Oort cloud, a structure we have never seen but infer must be there because the alternative, that comets simply appear from nowhere, makes no sense. There is something deeply strange about that. The Oort cloud is part of our address. It defines the outer boundary of the Sun's gravitational influence. It is, in a real sense, the edge of the solar system, and we know about it only because of math and because icy rocks occasionally fall out of it. NASA describes it plainly. The Oort cloud's existence is predicted based on mathematical models and observations of comets. Not confirmed, predicted. That is not a criticism. It is a reminder that even here, even in our own backyard, we are still working from inference and educated guesses. The solar system is not fully mapped. We do not have all the answers. Some of the most fundamental structures in our cosmic neighbourhood remain theoretical. The solar system formed from a dense cloud of interstellar gas and dust, roughly 4.5 billion years ago. That is the story we tell. And it is a good story, supported by evidence from meteorites, from planetary compositions, from the arrangement of orbits, and the chemical fingerprints of ancient rocks. But the details are messy. The early solar system was not a smooth, orderly process. It was violent, chaotic, shaped by collisions and migrations and gravitational bullying. The planets we see today are the survivors. The moons, the asteroids, the comets, they are the witnesses. The Kuiper Belt and the Oort cloud are the archives, holding on to material that never got incorporated into anything larger, preserving a record of what the solar system was made of before the planets finished forming. And all of it, every planet, every moon, every ring, every comet, is shaped by forces that operate on scales we struggle to visualize. Gravity pulls matter together and tears it apart. Magnetism channels charged particles into auroras and radiation belts. Radiation from the Sun strips atmospheres, carves surfaces, drives chemistry in ways that would never happen in the cold dark of deep space. Impacts deliver water and organic molecules and energy. Tidal forces need interiors, generating heat in places that should be frozen solid. The solar system is not a static collection of objects. It is a dynamic, interconnected system where everything affects everything else, where the history of one body is written into the geology of another, where the present is still being shaped by events that happened billions of years ago. We live in this system. We have lived here for as long as our species has existed. And for most of that time, we had no idea what any of it was. The planets were wandering lights. The moon was a circle in the sky. Comets were omens. It has taken us less than 500 years to go from thinking Earth was the centre of everything to sending robots to the edge of the solar system and beyond. We have landed on Titan. We have tasted the geysers of Enceladus. We have watched storms on Jupiter and flown through the rings of Saturn. And with every mission, every observation, every new measurement, the picture gets stranger. The solar system is not a solved problem. It is a collection of puzzles, some answered, most not. Why is Jupiter's great red spot so deep? Why is Saturn losing its rings? What knocked Uranus on its side? Is there life in Europa's ocean? What carved the channels on Titan? How many objects are hiding in the Kuiper belt? Does the Oort cloud look the way we think it does? We do not know, not yet. But we are looking, and every answer we find raises new questions, pushes the frontier of the unknown a little farther out. This is home, not just Earth, but the whole system. The sun, the planets, the moons, the belts of debris, the distant shell of comets we have never seen. All of it bound together by gravity, all of it shaped by the same physics, all of it part of the same story that began 4.5 billion years ago when a cloud of gas started to collapse. We are made of material from that cloud. The calcium in your bones, the iron in your blood, the oxygen you are breathing right now, all of it was forged inside stars that died before the sun was born. The solar system is not separate from us. We are part of it. We are one of the things it made, and the solar system itself is not separate from the rest of the universe. The sun is one star among hundreds of billions in the Milky Way galaxy. The material that built the planets came from earlier generations of stars. The forces shaping our cosmic backyard, gravity, electromagnetism, the nuclear reactions powering the sun, are the same forces operating in every other star system, every other galaxy, every corner of the cosmos. To understand the solar system is to start understanding how the universe works. And the next step in that understanding takes us beyond the neighbourhood, out into the vast stellar laboratories where stars are born, live, and die in ways that make Jupiter's storms look gentle by comparison. The solar system is our home, but it is not where the story begins, not really. Because before there was a solar system, before there was a sun, before there were planets or moons or comets, or any of the familiar architecture we just walked through, there was a cloud. And that cloud did not appear out of nowhere. It was made of material that came from somewhere else. From stars that lived and died long before our sun ever ignited. To understand where we came from, you have to understand what stars are, how they are born, how they live, and most importantly, how they die. Stars are not eternal. That is the first thing you need to accept. They look permanent. The constellations your great-great-grandparents saw are the same ones you see tonight. But that permanence is an illusion of scale. Stars are burning. Slowly, yes, but burning nonetheless. And everything that burns eventually runs out of fuel. The difference between a campfire and a star is not the principle. It is the time scale. A campfire burns for hours. A star burns for millions or billions of years. But the ending is the same. The fuel runs out, the fire goes out. What happens next depends entirely on how massive the star was to begin with, and that is where things get strange. Let's start at the beginning. Stars are born in nebulae. The word nebula is Latin for cloud, and that is exactly what they are. Giant clouds of gas and dust drifting through space. NASA describes them plainly. Nebulae are giant clouds of gas and dust in space. Some of them are regions where new stars are being born. Others are the expanding remnants of stars that have already died. The same structure can be both a cradle and a grave. That is not poetic language. It is literally what happens. A star dies, explodes, scatters its guts across space, and that material eventually gets swept up into a new cloud that collapses to form the next generation of stars. The cycle has been running for more than 13 billion years. Every star you see in the night sky is made, at least in part, from the remains of earlier stars. And when those stars die, their material will be recycled again. The process of star formation starts with gravity. A nebula is not uniform. It has dense regions and thin regions, clumps and voids. If one of those clumps gets dense enough, gravity starts to win. The clump pulls in more material. As it pulls in more material, it gets denser. As it gets denser, its gravity gets stronger. The process feeds itself. The clump collapses inward, slowly at first, then faster. As it collapses, it heats up. The particles are falling toward the center, picking up speed, colliding with each other. Collisions generate heat. The more the cloud collapses, the hotter the center gets. This collapsing clump is called a protostar. It is not yet a star. It is not yet fusing hydrogen into helium. It is just a ball of gas getting smaller and hotter. The collapse can take 1 million years or more. For most of that time, the protostar is hidden inside a dense cocoon of dust. You cannot see it in visible light. The dust blocks everything. But infrared telescopes can peer through the dust and watch the process unfold. What they see is chaos. Protostars do not collapse smoothly. They wobble. They spin. Material does not fall straight in. It spirals, forming a disk around the protostar. Some of that material gets flung outward in jets that shoot out from the poles at hundreds of kilometers per second. These jets carve tunnels through the surrounding cloud, sometimes stretching for light years. The protostar is fighting its own birth, throwing off material even as it pulls more in. Eventually, the core gets hot enough. The temperature climbs to around 10 million degrees Celsius. At that temperature, hydrogen nuclei are moving so fast that when they collide, they can overcome the electromagnetic repulsion that normally keeps them apart. They fuse. 2 hydrogen nuclei combine to form helium, releasing energy in the process. That energy pushes outward, counteracting the inward pull of gravity. The collapse stops. The protostar stabilizes. The star turns on. This is the moment of ignition. The star has entered what astronomers call the main sequence. It will stay there for most of its life, quietly fusing hydrogen into helium, balancing gravity against the outward pressure of nuclear fusion. Our Sun has been on the main sequence for about 4.5 billion years. It will remain there for another 5 billion or so. Main sequence stars are stable, predictable, boring by astronomical standards. But they are also the foundation of everything. Planets form around them. Life, if it arises, depends on them. The main sequence is where stars spend the vast majority of their existence. Not all stars are created equal. The mass of a star determines almost everything about its life. How hot it burns, how bright it shines, how long it lives, and how it dies. The smallest stars, red dwarfs, are only about 8% the mass of our Sun. They burn so slowly, so efficiently, that they can live for trillions of years. Trillions. The universe is only about 14 billion years old. That means every red dwarf ever born is still alive. None of them have had time to die yet. They will outlive every other type of star, outlive galaxies, outlive the current structure of the universe. And because they are so small and so dim, we cannot see most of them without a telescope. The nearest star to our solar system, Proxima Centauri, is a red dwarf. It is only 4 light years away. You cannot see it with your naked eye. At the other end of the spectrum are the blue giants and supergiants. These stars are monsters. Some of them are 10, 50, even 100 times the mass of our Sun. They burn hydrogen so fast, so furiously, that they can be 10,000 times brighter than our Sun. Some of the most extreme luminous stars reach far beyond even that. A star 100 million times brighter than the Sun is not a typo. It is real. These stars do not live long. A star with 50 solar masses might last only a few million years. That is nothing. Dinosaurs roamed Earth for longer than that. The trade-off for burning bright is burning fast. Massive stars sprint through their fuel and die young. When they die, they do not go quietly. Let's talk about stellar death, because this is where the universe gets interesting. A star like our Sun will eventually run out of hydrogen in its core. When that happens, fusion stops. The outward pressure drops. Gravity takes over again. The core contracts. As it contracts, it heats up. Eventually it gets hot enough to start fusing helium into carbon and oxygen. When that happens, the outer layers of the star expand, enormously. The Sun will swell into a red giant, growing so large that it will likely swallow Mercury, possibly Venus, maybe even Earth. The surface will cool, turning red, but the total energy output will increase. A red giant is not hotter than a main sequence star. It is just bigger, much bigger. Eventually the helium runs out too. The core contracts again. For a star like the Sun, that is the end of the line. It does not have enough mass to ignite the next stage of fusion. The core becomes a white dwarf, a dense ball of carbon and oxygen about the size of Earth, but with the mass of the Sun. The outer layers drift away as a planetary nebula, a glowing shell of gas expanding into space. The white dwarf sits at the centre, slowly cooling over billions of years. Eventually it will fade to black. A stellar ember, radiating no light, no heat, just drifting through space forever. That is the fate of low-mass stars. Quiet, unremarkable, final. Massive stars do not get that luxury. When a massive star runs out of hydrogen, it starts fusing helium, just like a sun-like star. But it does not stop there. It has enough mass, enough gravity, to keep the core contracting and heating up. Helium fuses into carbon. Carbon fuses into neon. Neon fuses into oxygen. Oxygen fuses into silicon. Silicon fuses into iron. Each stage happens faster than the one before. A massive star might spend millions of years fusing hydrogen. It might spend only a few 100,000 years fusing helium. By the time it gets to silicon, the process takes days, and then it reaches iron. Iron is the end. You cannot extract energy by fusing iron into heavier elements. The reaction costs energy instead of releasing it. So when the core fills with iron, fusion stops. There is no outward pressure. Gravity wins. The core collapses, and it does not collapse slowly. The collapse happens in less than a second. In that second, the core of a massive star, roughly the size of Earth, collapses to a sphere about 20 kilometers across. The density becomes so extreme that protons and electrons are crushed together, forming neutrons. The result is a neutron star, a ball of neutrons roughly the size of a city, with a mass between about 1.5 and 3 times the mass of our Sun. A sugar cube-sized chunk of neutron star material would weigh about 1 billion tons. The gravitational pull at the surface is so strong that if you tried to stand on it, you would be flattened into a layer of atoms 1 atom thick. Not that you would ever get close. You would be vaporized long before you landed. The collapse releases an unimaginable amount of energy. The outer layers of the star, suddenly unsupported, fall inward. They hit the incompressible neutron core and bounce. That bounce sends a shockwave ripping outward through the star at a significant fraction of the speed of light. The shockwave tears the star apart. This is a supernova. For a few weeks, a single exploding star can outshine an entire galaxy. Billions of stars outshone by one dying star. The explosion scatters the outer layers of the star across space at speeds of tens of thousands of kilometers per second. Everything the star spent millions of years building, carbon, oxygen, silicon, iron, gold, uranium, all of it gets flung into the surrounding interstellar medium. That material will eventually be swept up into new clouds, new protostars, new planetary systems. Every atom heavier than helium in your body was forged inside a star. Most of those atoms were scattered into space by a supernova. You are made of stardust. That is not a metaphor. It is a statement of fact. What is left behind after a supernova is the neutron star. And neutron stars are among the strangest objects in the universe. They are incredibly small. Roughly 20 kilometers across, about the size of a large city. They are incredibly dense. A teaspoon of neutron star material weighs as much as a mountain. They spin. Fast. When the core of a massive star collapses, it conserves angular momentum. Just like a figure skater spins faster when they pull their arms in, a collapsing stellar core spins faster as it shrinks. A lot faster. Some neutron stars spin hundreds of times per second. They also have magnetic fields. Enormous magnetic fields. NASA describes them as about 1 trillion times stronger than Earth's magnetic field. 1 trillion. Those magnetic fields channel charged particles into beams that shoot out from the neutron star's magnetic poles. If those beams happen to sweep across Earth as the neutron star spins, we detect a pulse. A regular rhythmic flash of radio waves, X-rays or gamma rays. These objects are called pulsars. The first pulsar was discovered in late 1967 by a graduate student named Jocelyn Bell Bernal. She was analysing radio telescope data from a survey of the sky when she noticed something odd. A signal that pulsed on and off with a period of about 1 1/3 seconds. Perfectly regular. At first, some of the team joked that it might be a signal from an alien civilization. They even nicknamed it LGM-1 for little green men. It was not aliens, it was a spinning neutron star. Follow-up observations found more pulsars, then more. The Vela pulsar, discovered shortly after, was the first pulsar linked directly to a known supernova remnant. It sits at the heart of the Vela supernova remnant, the expanding shell of gas left over from a star that exploded about 11,000 years ago. The discovery of pulsars was one of the great confirmations of theoretical astrophysics. Neutron stars had been predicted on paper decades earlier, but nobody knew if they actually existed. Pulsars proved they were real. Pulsars are lighthouses. That is the best analogy. They sit in the dark, spinning, sending out beams of radiation. If the beam happens to point at you, you see a flash. If it does not, you see nothing. The timing of those flashes is extraordinarily precise. Some pulsars keep time more accurately than the best atomic clocks on Earth. Astronomers have catalogued thousands of pulsars. Observed periods range from milliseconds to seconds. The fastest known pulsar spins more than 700 times per second. 700 rotations in 1 second. That is faster than a kitchen blender, and it is a ball of matter the size of a city with a mass greater than the Sun. The physics involved is so extreme that we still do not fully understand what is happening inside a neutron star. The density is so high that matter enters states that cannot be replicated in any laboratory. The core of a neutron star might contain exotic forms of matter that do not exist anywhere else in the universe. Quarks might be unbound, forming a quark soup. Or maybe not. We do not know. Neutron stars are physics laboratories that operate in regimes we cannot access. Every observation teaches us something new about how matter behaves under conditions we can barely imagine. And then there are the supernovae themselves. We need to pause on that because supernovae are not just spectacular light shows. They are the reason the universe looks the way it does. Without supernovae, there would be no heavy elements. No carbon, no oxygen, no iron, no anything beyond helium and traces of lithium. Stars fuse lighter elements into heavier ones, but most of those heavy elements stay locked inside the star. It takes a supernova to scatter them into space. Every carbon atom in your body, every oxygen molecule you breathe, every iron atom in your blood was created inside a star and flung into space by a supernova. The calcium in your bones came from a supernova. The gold in a wedding ring came from a supernova. Probably not the same supernova, but the principle holds. These explosions are not just destructive, they are generative. They seed the galaxy with the raw materials for planets, for chemistry, for life. Supernovae also trigger new star formation. The shockwave from an exploding star slams into nearby gas clouds, compressing them, triggering gravitational collapse. New stars are born in the wreckage of old ones. Nebulae are both stellar nurseries and stellar graveyards. NASA's summary captures it perfectly. Some stars are born in nebula. Some stars die there. The same cloud can witness both. The life cycle of stars is a cycle in the most literal sense. Death feeds birth. The remnants of one generation become the building blocks of the next. The universe recycles everything. There is something almost uncomfortable about how efficient the process is. Nothing is wasted. A star lives for millions or billions of years, burns through its fuel, fuses lighter elements into heavier ones, and when it dies, it gives everything back. The gas, the dust, the heavy elements, all of it gets returned to the interstellar medium. The next generation of stars incorporates that material, builds planets from it, and the cycle continues. The Sun is a third-generation star, maybe a fourth. It is made from material that has been through this cycle at least twice before. The Earth, the solar system, everything in it, is built from recycled stellar ash. We are not just made of stardust. We are made of reprocessed stardust, refined and enriched over billions of years by generations of stars we will never see. And the strange part is, this is all happening right now. Stars are being born. Stars are dying. Supernovae are exploding in distant galaxies, scattering heavy elements into space. New nebulae are collapsing, forming protostars, lighting up for the first time. The Milky Way produces a few new stars every year. Most of them are small, red dwarfs that will outlive the galaxy itself. Some are massive, blue giants that will explode within a few million years. The process is continuous. The universe is not static. It is dynamic, constantly building and destroying, creating and recycling. The stars you see tonight are not the same stars someone will see a billion years from now. Some will have died. New ones will have been born. The sky itself is changing, just too slowly for any human lifetime to notice. Here is the part that sits uncomfortably. We understand a lot of this. The life cycle of stars is one of the best understood processes in all of astronomy. We can model it. We can predict it. We can look at a star and tell you, with reasonable confidence, how long it will live and how it will die. But there are gaps, big ones. We do not know exactly what happens inside a neutron star. We do not fully understand how the supernova shockwave overcomes the infall of the outer layers. Early models predicted the shockwave would stall, that the explosion would fizzle out. It does not. Something is giving that shockwave an extra push, and we are still figuring out what. We do not know why some massive stars explode as supernovae and others collapse straight into black holes without any explosion at all. The line between the two is blurry. The details matter, and we do not have all of them yet. What we do have is a framework, a story that fits the observations. Stars are born in nebulae. They live on the main sequence, fusing hydrogen into helium. They age, expand, fuse heavier elements. They die, either as white dwarfs or in supernovae. They leave behind neutron stars, pulsars, and in some cases something even stranger. Because not every massive star ends as a neutron star. If the core is too massive, if the supernova does not blow off enough material, the collapse does not stop at a neutron star. Gravity wins completely. The core collapses past the neutron star stage. It collapses past any possible structure that could hold it up. It keeps collapsing until it becomes something that, by every law of physics we understand, should not exist. It becomes a black hole, a region where the gravitational pull is so strong that not even light can escape, a place where space and time themselves break down. And that is where the next part of the story begins. If the core is too massive, if the supernova does not blow off enough material, the collapse does not stop at a neutron star. Gravity wins completely. The core collapses past the neutron star stage. It collapses past any possible structure that could hold it up. It keeps collapsing until it becomes something that, by every law of physics we understand, should not exist. It becomes a black hole. Let's be clear about what that means. A black hole is not a hole. It is not empty space. It is not nothing. A black hole is mass, an enormous amount of mass, compressed into a volume so small that the numbers stop making intuitive sense. Take the mass of 10 suns and compress it into a sphere 20 kilometers across. Now keep compressing, smaller, smaller, until all that mass occupies a region with no size at all. A point, a singularity. That is what sits at the center of a black hole, and around that singularity space itself warps so severely that the rules change. Not metaphorically, literally. The fabric of space-time bends under the weight of all that compressed mass, and if you get close enough, the bending becomes so extreme that nothing, not even light, can climb back out. This is not a failure of engineering. It is not that we lack a fast enough rocket or a strong enough engine. It is that the escape velocity, the speed you would need to reach to break free, exceeds the speed of light, and nothing in the universe can travel faster than light. Not because we have not figured out how yet, because the universe does not allow it. The speed of light is a hard limit built into the structure of reality itself. So when you cross the boundary around a black hole where the escape velocity exceeds light speed, you have crossed a line you cannot uncross. That boundary has a name, the event horizon. NASA describes it plainly. Inside this boundary, the velocity needed to escape the black hole exceeds the speed of light. Once you're inside, you're not coming back. Not ever. The event horizon is not a physical surface. It is not made of anything. You could not touch it. You could not stand on it. It is just a location in space where the math changes, where the future stops, including any version of events in which you return to the outside universe. The term event horizon is uncomfortably appropriate, and horizon is the limit of what you can see. Stand on a hill and you can see to the horizon. Beyond that, the curve of the Earth blocks your view. The event horizon of a black hole is similar, except it is not about sight. It is about causality. Events that happen inside the event horizon cannot affect anything outside. Information cannot escape. Light cannot escape. Matter cannot escape. Nothing that crosses that boundary can return to the outside universe, not even light. That is a direct quote from the Center for Astrophysics at Harvard and Smithsonian. Not even light. If light cannot escape, then by definition, the region inside the event horizon is invisible. Black holes are not black because they are dark. They are black because they emit no light. They are invisible. The only way we know they are there is by watching what happens around them. Let's start with the simplest kind. Stellar mass black holes. These are the ones that form when a massive star collapses at the end of its life. We just walked through that process. The core collapses, bounces, triggers a supernova. If the core is not quite massive enough, it stops collapsing at the neutron star stage. If it is more massive, it keeps going. The exact threshold is not perfectly understood. Most models put it somewhere around 2.5 to 3 solar masses. A core more massive than that cannot stabilize as a neutron star. There is no force, no structure, no quantum pressure that can hold it up. Gravity crushes it into a singularity. The result is a stellar mass black hole. NASA describes stellar mass black holes as typically 5 to 10 times the mass of our Sun. Other educational sources place them in a broader range, a few to a few dozen solar masses. Either way, these are the smallest black holes we know about, formed from the deaths of individual stars. They are scattered throughout the galaxy. Most of them are invisible, drifting through space, pulling on nothing, detectable only if something happens to fall into them or orbit near them. Astronomers estimate there could be tens of millions of stellar mass black holes in the Milky Way alone. Most of them will never be directly observed. They are too small, too dark, too far away. The only ones we can detect are the ones that give themselves away by interacting with something nearby. The first stellar mass black hole ever identified was Cygnus X1, discovered in the early 1970s. Astronomers were studying X-ray sources in the sky when they noticed something odd, a powerful X-ray signal coming from the constellation Cygnus. Follow-up observations with optical telescopes revealed a blue supergiant star in the same location. The star was wobbling, not randomly, rhythmically, as if it were orbiting something, but there was nothing visible next to it. By measuring the wobble, astronomers calculated the mass of the invisible companion. It was too massive to be a neutron star. The only remaining option was a black hole. Cygnus X1 was the first black hole confirmed to exist outside of theoretical models. The X-rays were coming from the accretion disk, a swirling disk of gas and dust being pulled off the blue supergiant and spiraling into the black hole. As the material spirals inward, it heats up. It heats up a lot. Friction between particles in the disk generates temperatures of millions of degrees. At those temperatures, the gas emits X-rays. That is what astronomers detected. Not the black hole itself, but the glowing ring of doomed matter circling the drain. Accretion disks are one of the strangest structures in astrophysics. They form whenever matter falls toward a compact object, whether it is a black hole, a neutron star, or even a white dwarf. The material does not fall straight in. It has angular momentum. It is moving sideways relative to the center of mass. So instead of plunging directly into the black hole, it spirals. The closer it gets, the faster it moves. Near the event horizon of a stellar mass black hole, material in the inner edge of the accretion disk can be moving at a significant fraction of the speed of light. The disk itself can extend outward for thousands of kilometers or more, depending on how much material is available, and it glows. Not invisible light, usually. Most of the energy comes out as X-rays and ultraviolet radiation. But the brightest accretion disks can outshine entire stars. A black hole with 5 times the mass of the Sun, sitting at the center of a bright accretion disk, can emit more energy than 1,000 suns. The irony is hard to miss. Black holes are defined by the fact that they do not emit light. And yet some of the brightest objects in the universe are black holes. Or more precisely, the glowing halos of matter falling into them. Then there are the jets. Not every accreting black hole produces jets. But when they do, the results are spectacular. Jets are narrow beams of matter and energy launched from the region near the black hole's poles. NASA notes that some jets fire particles at close to the speed of light. Some reviews describe active galactic nucleus jets, which we will get to shortly, as longer than 10 million light years and faster than 0.9 times the speed of light. 10 million light years. That is a beam of matter stretching across intergalactic space, fired by a black hole sitting at the centre of a galaxy. Jets are one of the most energetic phenomena in the universe, and we still do not fully understand how they form. Here is what astronomers think is happening. Material in the accretion disk spirals inward. As it does, magnetic fields threading through the disk get twisted and amplified. These magnetic fields channel some of the infalling material away from the disk, accelerating it to enormous speeds and flinging it outward along the black hole's rotational axis. The process is called magnetic launching, and the details are still being worked out. What is clear is that jets are incredibly efficient at transporting energy and angular momentum away from the black hole. They can extend for thousands of light years, punching through the interstellar medium, heating gas clouds, triggering or suppressing star formation, reshaping entire regions of a galaxy. Jets are not just side effects, they are active players in galactic evolution. A black hole with jets is not passively sitting in space. It is reaching out, influencing its surroundings on scales far beyond its immediate gravitational reach. Despite all the observations, despite decades of study, astronomers still do not fully understand how black holes produce jets. The broad picture involves magnetic fields and rotating accretion disks. The fine details, the exact mechanism that accelerates particles to near light speed and collimates them into narrow beams, remain murky. We can see the jets, we can measure their speed, their energy, their composition, we can model pieces of the process, but a complete start-to-finish explanation is still out of reach. Black holes are fundamentally strange objects, and jets are one of the clearest reminders that we are still figuring out how they work. Let's talk about what happens if you fall into one. This is where things get uncomfortable. Imagine you're in a spacecraft drifting toward the event horizon of a stellar mass black hole. You're falling feet first. As you get closer, the gravitational pull on your feet becomes noticeably stronger than the pull on your head. This difference in gravitational force is called a tidal force. On Earth, tidal forces from the Moon cause the oceans to bulge. Near a black hole, tidal forces are strong enough to stretch you. Literally, your body elongates, your feet are pulled harder than your head. The closer you get, the worse it gets. Eventually, the difference becomes so extreme that your body is pulled apart. Astronomers have a term for this: spaghettification. You're stretched into a long, thin strand like a piece of spaghetti. By the time you reach the event horizon, you're not recognizable as a human anymore. You're a stream of atoms, a column of disassociated matter spiraling into the black hole. This is not speculation. This is what the math predicts happens to any object that falls into a black hole, assuming the black hole is small enough that the tidal forces near the horizon are strong. Here is the strange part. If you were somehow watching from a safe distance, you would never see your friend cross the event horizon. As they fall closer, time dilation kicks in. Clocks near the event horizon run slower compared to clocks far away. From your perspective, your friend's fall slows down. They get closer and closer to the horizon, but they never quite reach it. Their image freezes, redshifts, fades, but they never cross. They appear to be stuck at the edge, frozen in time, slowly dimming until they disappear. From your friend's perspective, assuming they somehow survived spaghettification, the experience is different. They cross the event horizon in a finite amount of their own time. Nothing dramatic happens at the moment of crossing. There is no wall, no barrier. The event horizon is just a location, but once they cross it, every direction they try to move leads inward. Up, down, left, right, forward, backward, all directions point toward the singularity. The future becomes a place, and that place is the center of the black hole. There is no way out because every possible path through space-time leads deeper in. This is not a limitation of technology, it is a property of the geometry itself. The black hole has reshaped space-time so severely that escape is not just difficult. It is not a thing that the word escape can describe anymore. What happens at the singularity no one knows. General relativity predicts that all the infalling matter gets crushed into a point of infinite density. Infinite. That is a word physicists hate to see in their equations. Infinities usually mean the theory has broken down, that you're asking it to describe something it was not built to handle. Most physicists believe that quantum mechanics, the physics of the very small, will step in and modify what happens at the singularity. Maybe the collapse stops at some incredibly tiny but finite size. Maybe space-time itself becomes grainy or foamy at that scale. Maybe something else happens that we do not have the math to describe yet. The point is, we do not know. The singularity is hidden inside the event horizon. We cannot see it. We cannot probe it. We cannot send a signal out from it. It is fundamentally cut off from the rest of the universe. Whatever happens there, stays there. Stellar mass black holes are strange, but they are small compared to what sits at the centres of galaxies. Supermassive black holes, these objects are in a completely different category. They span roughly 100,000 to billions of solar masses. Billions. Our own Milky Way galaxy has one. It is called Sagittarius A star, and it weighs about 4 million times the mass of our Sun. For a long time, astronomers suspected it was there based on the motion of stars near the centre of the galaxy. Stars were orbiting something visible, something with a lot of mass. By tracking the orbits of individual stars over decades, astronomers calculated the mass of the object they were orbiting. The numbers pointed to a black hole. In 2002, astronomers using the Very Large Telescope in Chile tracked a star called S2 as it made a close approach to Sagittarius A star. The star reached speeds of more than 5,000 kilometers per second, roughly 1.5% the speed of light, as it whipped around the black hole. The observations were so precise that they could measure the relativistic effects predicted by general relativity. The black hole was bending spacetime, and the stars were following the curves. Sagittarius A star is quiet. It is not actively feeding. There is very little material in the accretion disk. Occasionally, a gas cloud or an unlucky star wanders too close and gets shredded, producing a brief flare of X-rays or radio waves. But most of the time, the black hole at the centre of our galaxy is just sitting there, pulling on the stars around it, doing nothing dramatic. That is not the case for all supermassive black holes. Some of them are feeding, vigorously. When a supermassive black hole is actively accreting material, the accretion disk can become one of the most luminous objects in the universe. The term for a galaxy with an actively feeding supermassive black hole at its centre is active galactic nucleus, or AGN. Some AGNs are so bright that they outshine the rest of the galaxy combined. Billions of stars outshone by the glowing disk of matter spiralling into the central black hole. AGNs come in different varieties depending on how you are looking at them. Quasars, blazars, Seyfert galaxies, radio galaxies. The distinctions have to do with orientation, the angle at which we are viewing the AGN, and the specifics of what is going on in the accretion disk and the jets. Quasars are the brightest. They are AGNs viewed more or less face-on, where we are looking straight down into the accretion disk. The light from the disk, amplified by the sheer amount of material being consumed, can make a quasar visible across billions of light years. Some of the most distant objects we have ever observed are quasars. We are seeing them as they existed when the universe was less than 1 billion years old. The light has been travelling toward us for more than 13 billion years, and when it left its source, the quasar was already shining with the light of trillions of suns. Blazars are even stranger. These are AGNs, where one of the jets is pointed almost directly at us. The jet is moving at close to the speed of light, aimed straight at Earth. The result is a relativistic beaming effect. The light from the jet gets compressed and amplified, making the blazar appear extraordinarily bright. Blazars are some of the most variable objects in the sky. They can flare up by factors of 10 or more in a matter of days or even hours. The variability tells us that the region producing the light is small. If the flare happens over the course of a day, the emitting region cannot be larger than about 1 light day across. Otherwise, the light from different parts of the region would arrive at different times and smear out the signal. A region 1 light day across is tiny compared to the size of a galaxy. We are watching processes happening on scales of billions of kilometers, driven by a black hole weighing billions of solar masses and producing enough energy to outshine the entire host galaxy. The physics involved is extreme. The observations are unambiguous. The explanations are still being refined. Supermassive black holes sit at the centres of nearly every large galaxy. Not most, nearly every. Observations over the past few decades have made this clear. Whether the galaxy is a spiral like the Milky Way, or an elliptical like M87, whether it is active or quiet, whether it is young or old, there is almost always a supermassive black hole at the centre. The mass of the black hole correlates with the mass of the galaxy's central bulge, the dense region of stars surrounding the galactic core. This correlation is not perfect, but it is strong enough that astronomers think the growth of the black hole and the growth of the galaxy are linked. They evolve together. How exactly that happens is still being worked out. But the connection is real. The existence of supermassive black holes raises an obvious question. How did they get so big? A stellar mass black hole forms from the collapse of a single massive star. You start with a star, it dies, you get a black hole. Simple. A supermassive black hole weighing billions of solar masses cannot form that way. There is no star that massive. You cannot collapse a single object and get a billion solar mass black hole. So where did they come from? There are a few ideas, none of them completely satisfying. The first idea is that supermassive black holes started as stellar mass black holes and grew by accretion. They pulled in gas, dust, stars, anything that wandered too close. Over time, they gained mass. A black hole that starts at 10 solar masses and accretes material at a steady rate can double in mass every few tens of millions of years. Run that process for a few billion years, and you can grow a very large black hole. The problem is that some supermassive black holes existed less than a billion years after the Big Bang. We have observed quasars at distances corresponding to when the universe was only a few hundred million years old. Those quasars are powered by black holes weighing hundreds of millions or even billions of solar masses. There was not enough time for a stellar mass black hole to grow that large by accretion alone. The math does not work. You would need to accrete material faster than the theoretical limit, or you would need to start with a much larger seed. That brings us to the second idea, direct collapse. In this scenario, giant clouds of primordial gas in the early universe collapse straight into black holes without forming stars first. If the conditions were right, if the gas was hot enough and dense enough, it could skip the star formation process entirely and collapse into a black hole of maybe 100,000 solar masses or more. Starting with a seed that large gives you a huge head start. Grow from there by accretion and mergers, and you can reach billions of solar masses within the time available. The challenge is that direct collapse requires very specific conditions. The gas has to be metal poor, meaning it contains almost no elements heavier than helium. It has to be hot enough to resist fragmenting into smaller clumps that would form stars. And it has to collapse fast enough to avoid cooling and fragmenting. We do not know how common those conditions were in the early universe. The idea is plausible, but it is still speculative. The third idea is mergers. Black holes can merge with each other. When two galaxies collide, their central black holes eventually sink toward the center of the merged galaxy and combine. The result is a larger black hole. Repeat that process enough times, and you can build a supermassive black hole from smaller pieces. This almost certainly happens. We have indirect evidence of black hole mergers from gravitational wave detections. The problem, again, is time. Building a billion solar mass black hole purely through mergers requires a lot of mergers, and each merger takes time to set up. The black holes have to lose enough orbital energy to spiral together, which usually happens through interactions with stars and gas. The timescale for that process is long, too long to explain the supermassive black holes we see in the very early universe. Mergers are part of the story, but they cannot be the whole story. The honest answer is that we do not know how supermassive black holes formed. All three mechanisms, accretion, direct collapse, and mergers, probably played a role. The relative importance of each is still being debated. Every new observation of a distant quasar or an unexpectedly massive black hole in the early universe adds another data point, and every data point makes the picture a little more complicated. Here is what we do know. Black holes exist. Stellar mass black holes are the remnants of massive stars. Supermassive black holes sit at the centers of galaxies, shaping their evolution, driving jets that reach across intergalactic space, powering some of the most luminous objects in the universe. The event horizon is a real boundary, the point beyond which nothing can return. Accretion disks glow because in falling matter heats up. Jets are launched by processes we are still trying to fully understand, and black holes are effectively invisible because light cannot escape from inside the event horizon. Everything we know about them comes from watching what happens nearby. The wobbling of stars, the glow of accretion disks, the trajectories of jets, the gravitational waves emitted when two black holes merge. We are mapping the invisible by studying its effects on the visible. Black holes are extreme. They are the logical conclusion of gravity taken to its limit. They warp spacetime so severely that the usual rules stop applying. They challenge our intuitions about space, time, causality, and the nature of matter, and they are not rare. They are everywhere. Scattered through galaxies, anchoring galactic centres, shaping the large-scale structure of the universe. We live in a universe where black holes are a normal part of the furniture. That should be strange. Maybe it is. Or maybe it is just another reminder that the universe operates on principles that do not care whether they make sense to us. The next step outward takes us beyond individual stars, beyond individual black holes, to the structures those objects build. Because stars do not drift alone through space. They cluster, they gather, they form bound systems held together by gravity, systems so large that light takes tens of thousands, or even hundreds of thousands of years to cross them. Galaxies, islands of stars floating in the void. And each one contains billions or even trillions of stars, along with gas, dust, planets, black holes, and structures we are only beginning to understand. You live in one, the Milky Way, a spiral galaxy roughly 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars. The uncertainty in that number is not a rounding error. It is a reflection of how difficult it is to count stars when you are sitting inside the thing you are trying to measure. Imagine trying to map your city while standing in the middle of it, unable to move, unable to see through buildings, with half the streets hidden by fog. That is the situation astronomers face when studying the Milky Way. We are embedded in the disk, surrounded by dust with no external vantage point. Everything we know about the structure of our own galaxy has been pieced together from observations made from the inside, looking out through layers of gas and stars and debris. The Milky Way is a barred spiral galaxy. That means it has a central bar-shaped structure made of stars, with spiral arms winding outward from the ends of the bar. Our solar system sits roughly 26,000 light-years from the centre, out in one of the spiral arms. The arms are not solid structures. They are density waves, regions where stars and gas are temporarily bunched together as they orbit the galactic centre. Stars move in and out of the arms over millions of years. The arms persist because the density wave persists, like a traffic jam that stays in the same place, even though individual cars move through it. The Milky Way has several major spiral arms and a handful of smaller ones. We live in a minor arm called the Orion Spur, a short branch connecting two larger arms. Not the suburbs exactly, more like the exurbs. A quiet neighbourhood far from the action. The centre of the galaxy is not quiet. At the very core, 26,000 light-years from where you are sitting, there is a supermassive black hole, Sagittarius A star. We talked about it in the last chapter. 4 million solar masses, surrounded by a dense cluster of stars, some of them orbiting so close to the black hole that they complete a full orbit in under 20 years. One of those stars, called S2, has been tracked by astronomers for decades. In 2018, it made its closest approach to Sagittarius A star, passing within about 17 light-hours of the event horizon. 17 light-hours. That is roughly 4 times the distance from the Sun to Pluto. At that distance, the black hole's gravity is so strong that relativistic effects become measurable. Time dilation, gravitational redshift, the bending of the star's trajectory in ways that Newtonian gravity cannot explain. General relativity predicts all of it. The observations confirmed it. S2 is a laboratory for testing Einstein's equations in one of the most extreme gravitational environments we can observe, and it happens to be orbiting the black hole at the centre of our galaxy. Sagittarius A star is quiet most of the time. It is not actively feeding. There is very little material in the immediate vicinity for it to accrete. Occasionally something wanders too close. A gas cloud maybe, or an unlucky star that gets torn apart by tidal forces. When that happens, the black hole flares briefly in X-rays or radio waves. But for the most part, the centre of the Milky Way is calm. That is not the case for all galaxies. Some of them have central black holes that are feeding voraciously, pulling in enormous amounts of gas and dust, glowing so brightly that they outshine the rest of the galaxy. We will get to those in a moment. The Milky Way is not alone. It is part of a small group of galaxies called the Local Group, which contains about 80 galaxies in total. Most of them are dwarf galaxies, small systems with only a few billion stars or less. The two dominant members of the local group are the Milky Way and the Andromeda Galaxy, a spiral galaxy slightly larger than our own, sitting about 2.5 million light-years away. Andromeda is the most distant object you can see with your naked eye. On a clear dark night far from city lights, it appears as a faint smudge in the constellation Andromeda. That smudge is an entire galaxy, 1 trillion stars roughly. You are seeing photons that left Andromeda 2.5 million years ago, when early humans were just starting to use stone tools. The light has been travelling through space for longer than our species has existed in its current form, and when it finally reaches your eye, your brain interprets it as a faint patch of glow in the night sky. The Milky Way and Andromeda are on a collision course. They are moving toward each other at about 110 kilometers per second. In roughly 4 to 5 billion years they will collide. Not collide in the sense that stars will smash into each other. Space is vast, stars are tiny. The odds of two stars actually hitting each other during a galactic collision are astronomically small. But the galaxies will pass through each other, their gravitational fields pulling and stretching and distorting the structure of both. Stars will be flung into new orbits. Gas clouds will collide, triggering bursts of star formation. The spiral arms will be disrupted. Over hundreds of millions of years, the two galaxies will merge, eventually forming a single large elliptical galaxy. Astronomers have even given it a nickname, Milkomeda. The Milky Way as we know it will be gone. Andromeda will be gone. What remains will be something new, a scrambled mix of both. Our solar system will likely survive the merger. The Sun is not massive enough to be pulled into the central black hole, and the odds of a close encounter with another star are low. But the sky will look different. The familiar disk of the Milky Way, that band of light stretching across the night sky, will be replaced by a more diffuse glow as the solar system is flung into the outer halo of the merged galaxy. By then, the Sun will be nearing the end of its life anyway. The collision is not a threat to us. It is just a reminder that galaxies are not static. They move, they interact, they evolve. Galaxies come in a few basic shapes. The classification scheme was developed by Edwin Hubble in the 1920s and is still in use today, with some refinements. Hubble divided galaxies into 3 main types: spirals, ellipticals, and irregulars. Spiral galaxies like the Milky Way and Andromeda have a flat disk of stars, gas, and dust, with spiral arms winding outward from the centre. The disk is where most of the star formation happens. Gas clouds collapse, form stars, and those stars light up the spiral arms. The centre of a spiral galaxy usually contains a bulge, a dense spherical region of older stars. Some spirals, like the Milky Way, also have a bar-shaped structure in the middle. Others do not. The distinction is not trivial. Bars affect the flow of gas in the galaxy, funneling material toward the centre, which can trigger star formation or feed the central black hole. Roughly 2/3 of spiral galaxies have bars. The Milky Way developed its bar relatively recently, within the last few billion years. We know this because the orbits of stars in the bar are different from the orbits of stars in the disk. The bar is a dynamic structure, not a permanent feature. Elliptical galaxies are different. They have no disk, no spiral arms, very little gas and dust, and almost no ongoing star formation. They are smooth, featureless, shaped like ellipsoids. Some are nearly spherical, others are elongated like a rugby ball. Ellipticals range in size from dwarf ellipticals, which are tiny, to giant ellipticals, which can contain trillions of stars. The largest galaxies in the universe are ellipticals. They sit at the centres of galaxy clusters, having grown fat by cannibalizing smaller galaxies over billions of years. The stars in elliptical galaxies are old. Most of them formed billions of years ago, when the galaxy was young and still had gas to make new stars. Once the gas was used up or blown out by supernova explosions and winds from the central black hole, star formation stopped. What remains is a population of aging stars slowly fading, with no new generation to replace them. The shape of a galaxy tells you its history. Spirals are actively forming stars. They have gas, they have a disk, which means they have not been violently disrupted recently. Ellipticals, on the other hand, look the way they do because they have been through collisions. When two spiral galaxies collide, their disks are disrupted. Stars are flung into random orbits. The gas is either used up in a burst of star formation or blown out of the galaxy entirely. What is left is an elliptical, a a disordered swarm of stars with no coherent rotation, no disk, no structure. Galaxy shape is not just about appearance, it is about what has happened to the galaxy over billions of years. Every elliptical galaxy you see is the remnant of a merger. Every spiral galaxy is one that has managed to avoid major collisions long enough to maintain its disk. Then there are the irregulars. Galaxies with no clear shape, no symmetry, no disk or bulge or spiral arms, just a chaotic mess of stars and gas. Irregular galaxies are usually small. Many of them are dwarf galaxies, systems with only a few billion stars. Some irregulars are galaxies that have been disrupted by gravitational interactions with a larger neighbour. Others are young galaxies that have not yet settled into a stable structure. The Small Magellanic Cloud and the Large Magellanic Cloud, two satellite galaxies orbiting the Milky Way, are classified as irregulars. You can see them with the naked eye from the southern hemisphere. They look like detached pieces of the Milky Way floating nearby, which in a sense they are. Both are being slowly torn apart by the Milky Way's gravity. Eventually they will be absorbed. Galaxies do not float in isolation. They cluster. The Milky Way is part of the local group. The local group is part of a larger structure called the Virgo supercluster. And the Virgo supercluster is part of an even larger structure called Laniakea. These are not formal, sharp boundaries. They are regions of space where galaxies are more densely packed than average, held together by their mutual gravity. At the centre of the Virgo supercluster sits the Virgo cluster, a collection of more than 1,000 galaxies crammed into a region about 15 million light-years across. The Virgo cluster is massive. Its gravity dominates the local region of space, pulling nearby galaxies toward it. The Milky Way is being pulled toward the Virgo cluster right now, not falling in exactly. More like drifting in that general direction under the influence of a gravitational tug we cannot resist. The journey will take billions of years. By the time we get there, the Milky Way will have already merged with Andromeda. Laniakea is even larger. The name means immeasurable heaven in Hawaiian, which gives you some idea of the scale. Laniakea contains roughly 100,000 galaxies spread across 500 million light-years. It is not a gravitationally bound system. The galaxies within it are not all orbiting a common centre, but they are all part of the same large-scale flow of matter, the same cosmic river moving together through space. The structure was only mapped in 2014, using data on the velocities of galaxies within the region. Astronomers traced the motion of galaxies backward, identifying the directions from which they were being pulled, and found that they all seemed to be flowing toward a single point. That point, the gravitational centre of Laniakea, is called the Great Attractor. It is not a single object. It is a region of space where an enormous amount of mass is concentrated, pulling everything nearby toward it. The Great Attractor is hidden behind the plane of the Milky Way, obscured by dust and stars. We cannot see it directly, but we can see its effects. Galaxies for hundreds of millions of light-years around are all moving toward it. Galaxy clusters are the largest gravitationally bound structures in the universe. Some clusters contain thousands of galaxies packed into regions a few million light-years across. The space between galaxies in a cluster is not empty. It is filled with hot gas, heated to tens of millions of degrees by the gravitational energy of the cluster. This gas, called the intracluster medium, is so hot that it glows in X-rays. Most of the normal matter in a galaxy cluster is not in the galaxies themselves, it is in the gas between them, and even that is dwarfed by the dark matter. Observations of galaxy clusters show that the visible matter, stars and gas, makes up only a small fraction of the total mass. The rest is dark matter, the invisible substance that does not emit or absorb light but makes its presence known through gravity. We will get to dark matter later. For now, the point is that galaxy clusters are dominated by things we cannot see. The galaxies are just tracers, bright markers floating in a sea of dark matter. Galaxies within clusters collide frequently. Not all the time, but often enough that collisions are a normal part of cluster life. When two galaxies collide, the process takes hundreds of millions of years. They approach each other, pass through each other, their gravity pulling stars and gas into tidal tails that stretch for hundreds of thousands of light years. Some of the gas collides, heats up, and triggers bursts of star formation. Some of it is blown out of the galaxies entirely, adding to the intracluster medium. The galaxies loop around each other bound by gravity, gradually losing orbital energy as they interact with the surrounding cluster. Eventually they merge, forming a single larger galaxy. This process, repeated over billions of years, is how the largest galaxies in the universe are built. Galaxy mergers are not rare catastrophic events. They are how galaxies grow. The Milky Way and Andromeda merger is just one example. There are others happening right now. The Antennae galaxies, a pair of spiral galaxies about 45 million light-years away, are in the process of colliding. The collision has pulled out long tidal tails of stars and gas that stretch for hundreds of thousands of light-years, giving the system the appearance of an insect's antennae. Hubble Space Telescope images show the collision in detail: massive star-forming regions, clusters of young bright stars scattered throughout the merging galaxies. The collision has triggered a starburst, a period of intense star formation, as gas clouds are compressed and shocked by the interaction. In a few 100 million years, the two galaxies will merge completely. The tidal tails will fade. What remains will be a single elliptical galaxy, its disk destroyed, its star formation extinguished. For a long time, astronomers thought they had a pretty good handle on how many galaxies exist in the observable universe. The number usually quoted was around 100 to 200 billion. That estimate came from deep surveys conducted by the Hubble Space Telescope, combined with models that extrapolated from what Hubble could see to what lay beyond its reach. 100 billion galaxies. That was the standard figure. It showed up in textbooks, in documentaries, in popular science articles. It was the number everyone used. And then in 2016, a team led by Christopher Consolis published a study that revised that number upward, dramatically. Consolis' team used data from Hubble Deep Field observations, some of the longest and most sensitive images ever taken of distant regions of the universe. They counted galaxies in those images, then used mathematical models to account for the galaxies that were too faint or too distant for Hubble to detect. The analysis revealed something unexpected. The number of galaxies Hubble could see was only a small fraction of the total. Most galaxies in the universe are too small, too dim, or too far away to show up in even the deepest images. When Consolis' team extrapolated their counts to include those missing galaxies, the number climbed, way up. The conclusion was stark. The observable universe contains at least 2 trillion galaxies, not 100 billion, 2 trillion. That is 10 times the previous estimate. 10 times. Let that sit for a moment. 2 trillion galaxies, each one containing anywhere from a few million to several trillion stars. Each one separated from its neighbours by millions of light-years of empty space. The observable universe is roughly 93 billion light-years across. Within that volume, there are 2 trillion islands of stars, each one a galaxy, each one containing billions or trillions of suns, and most of them are too faint for us to see. Hubble, one of the most powerful telescopes ever built, can only detect a small fraction of them. The rest are out there, hidden in the noise, too distant or too dim to register, but they are there. The math says they have to be. The missing galaxies are not mysterious in the sense that we do not know what they are. They are small, low-mass galaxies, dwarf galaxies most likely, systems with only a few million or a few billion stars. Individually, they are faint. Collectively, they dominate the galaxy population. Think of it like a census of a city. If you only count the skyscrapers, you will miss most of the buildings. The small houses, the apartments, the shops, those make up the bulk of the urban landscape. The same is true for galaxies. The big bright galaxies, the ones we can see easily, are the skyscrapers. The dwarf galaxies are the houses. There are a lot more houses than skyscrapers, and until 2016, we were drastically undercounting them. The 2 trillion number is an estimate. It is based on models. Those models make assumptions about the distribution of galaxy masses, the rates at which galaxies merge, and the detectability limits of our telescopes. Some later analyses have suggested the number could be even higher. Estimates ranging from 6 trillion to 20 trillion have appeared in popular summaries, though those figures are less rigorously derived. The point is not the exact number. The point is that the universe contains far more galaxies than we thought, and most of them are too faint for us to see directly. We know they are there because the math requires them to be there, but we cannot point a telescope at most of them and take a picture. They are invisible to us, hidden in the deep background of space, contributing to the overall structure of the universe, but too faint to resolve as individual objects. This changes the way we think about the universe. 2 trillion galaxies means 2 trillion separate environments, 2 trillion places where stars are born and die, where planets form, where chemistry happens. It means the universe is vastly more crowded, vastly more complex than earlier estimates suggested. And it means that everything we can see, all the galaxies Hubble has imaged, all the stars we have studied, all the planets we have detected, represent only a tiny fraction of what is out there. Most of the universe is invisible to us, not because it is hidden by distance or dust, but because it is too faint. We do not have the instruments to see it. Not yet. Galaxies are not static. They evolve. They grow through mergers. They form stars, exhaust their gas, and fade. The rate of star formation across the universe has been declining for billions of years. The universe was more active when it was younger. Galaxies formed stars faster. Gas was more abundant. Collisions were more frequent. Today, star formation has slowed. Many galaxies have used up most of their gas. The largest ellipticals are no longer forming stars at all. The universe is aging. The peak of star formation happened roughly 10 billion years ago. Since then, the rate has been dropping. In the far future, billions of years from now, star formation will cease almost entirely. The universe will be filled with old, fading stars, with no new generation to replace them. The galaxies we see today, bright and active, will fade to dark. The universe will grow cold and dim. But that is a long way off. For now, galaxies are still vibrant, still evolving, still producing stars and planets and black holes, and all the structures that make the universe interesting. The discovery of 2 trillion galaxies is a reminder that we are still learning the basics. We thought we knew how many galaxies existed. We were off by a factor of 10. That is not a small error. It is a fundamental misunderstanding of the scale of the cosmos, and it happened because we reached the limits of what our telescopes could see and assumed we were seeing most of what was there. We were not. The James Webb Space Telescope, with its larger mirror and greater sensitivity, is beginning to push past those limits. Webb can see fainter galaxies, more distant galaxies, galaxies that were invisible to Hubble. Every new observation refines the picture, and every refinement reveals that the universe is larger, stranger, more populated than we thought. Galaxies are the building blocks of the universe. They are where stars form, where planets coalesce, where chemistry becomes complex enough to produce molecules, maybe even life. Every star you see in the night sky is part of the Milky Way. Every galaxy you see through a telescope is an island of stars, floating in the void, separated from its neighbours by millions of light years. And beyond the galaxies we can see, there are trillions more, too faint or too distant to detect, but no less real. They're out there. We're beginning to understand just how vast the universe really is, and the more we learn, the smaller our corner of it seems. The next question, the one that follows naturally from all of this, is whether we are alone. 2 trillion galaxies, trillions of stars in each galaxy. The numbers suggest that planets are common. Chemistry is common, energy is common. Water, carbon, all the ingredients for life as we know it, exist throughout the universe. So where is everybody? That is the question this chapter is built around. Not galaxies. Not stars, worlds, the search for planets orbiting other stars, the hunt for signs of life beyond Earth, and the uncomfortable silence that so far has greeted every attempt to find it. For most of human history, the only planets we knew about were the ones in our solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. 8 planets orbiting one star. That was it. That was the entire catalogue. Astronomers suspected that other stars might have planets, but suspicion is not the same as evidence. You cannot see a planet orbiting another star with the naked eye. You cannot see one through a small telescope. Even through the most powerful telescopes available in the early 20th century, planets around other stars remained invisible. Too small, too faint, too close to their host stars. The light from the star drowns out the light from the planet by a factor of billions. Trying to see an Earth-like planet next to a Sun-like star from dozens or hundreds of light years away is like trying to spot a firefly next to a searchlight from across an ocean. The glare is overwhelming. The planet disappears in the noise, so astronomers got clever. If you cannot see the planet directly, look for its effects. Look for what it does to the star. A planet orbiting a star tugs on that star with its gravity. The star does not sit perfectly still at the centre of the solar system. It wobbles, slightly. The wobble is tiny. For a planet the size of Jupiter orbiting a Sun-like star, the wobble amounts to a change in the star's velocity of about 12 meters per second. That is about the speed of a running human. For an Earth-mass planet, the wobble is closer to 10 centimeters per second. That is slower than a crawling baby. Detecting that kind of motion from hundreds of light years away requires extraordinary precision. But it is possible. The technique is called the radial velocity method, also known as the Doppler wobble method. As the star moves toward us, its light shifts slightly toward the blue end of the spectrum. As it moves away, the light shifts toward red. By measuring those tiny shifts in the star's spectrum, astronomers can infer the presence of a planet they cannot see. The first confirmed detection of a planet orbiting a Sun-like star using this method came in 1995. The star was called 51 Pegasi, a Sun-like star about 50 light-years away in the constellation Pegasus. The planet was called 51 Pegasi b, and it was nothing like what anyone expected. 51 Pegasi b is a gas giant, roughly half the mass of Jupiter. That part was not surprising. Gas giants were expected. What was surprising was the orbit. The planet completes one orbit around its star in just over 4 days. 4 days. Jupiter takes 12 years to orbit the Sun. This planet was orbiting so close to its star that its atmosphere was likely being heated to over 1,000 degrees Celsius. The discovery turned planetary science on its head. Nobody thought gas giants could exist that close to a star. The prevailing theory was that gas giants form far from their stars, where it is cold enough for ice to condense, and then maybe migrate inwards slightly over time. But 4-day orbits? That was not slight migration. That was something else entirely. 51 Pegasi b opened a new category of planets. Hot Jupiters. Gas giants orbiting absurdly close to their stars, tidally locked, with one side permanently facing the star and the other in eternal night. These planets should not exist. And yet there they were, showing up in survey after survey once astronomers knew to look for them. The radial velocity method works. It has found hundreds of planets, but it has limitations. It is biased toward massive planets in close orbits because those produce the largest wobbles. Small planets far from their stars produce wobbles too tiny to detect with current instruments. And the method tells you very little about the planet itself. You get a minimum mass and an orbital period. That is it. You do not get a size. You do not get a composition. You do not know if it has an atmosphere or what that atmosphere is made of. For that, you need a different technique. The transit method. A transit happens when a planet crosses in front of its star as seen from Earth. When that happens, the planet blocks a small fraction of the star's light. The star dims slightly. For an Earth-sized planet transiting a Sun-like star, the dimming is about 0.01%, 1 part in 10,000. That is a candle flickering in a floodlight. Detecting that kind of signal requires a telescope that can measure the brightness of a star with extraordinary precision over long periods of time. And it requires that the planet's orbit be aligned just right. If the orbit is tilted so that the planet passes above or below the star from our perspective, you will never see a transit. The geometry has to be edge-on. For any given star, the odds of that alignment are low. But if you watch enough stars, you will find transits. The first transit detections were made in 1999. By the early 2000s, the technique was starting to produce results, and then NASA launched Kepler. The Kepler Space Telescope launched in 2009 with one job: stare at a single patch of sky containing about 150,000 stars and watch for transits. Do not look anywhere else, just stare, for years. Kepler did exactly that. It measured the brightness of those stars every 30 minutes, building up a continuous record of tiny brightness variations. When a planet transited, Kepler saw it. And when the planet completed its orbit and transited again, Kepler saw that too. The periodic dimming, the repeating pattern, that was the signature of a planet. Kepler found thousands of them. By the time the mission ended in 2018, Kepler had detected more than 2,700 confirmed exoplanets and identified thousands more candidates awaiting confirmation. As of July 2026, the NASA Exoplanet Archive listed 6,324 confirmed exoplanets. Most of those came from Kepler or its successor missions. The transit method has produced the largest share of known exoplanets. It is not because transits are the easiest thing to detect. They are not. It is because the method works on a large scale. You can watch thousands of stars at once sifting through the noise to find the planets hiding in the data. Transit data tells you more than radial velocity does. You get the planet's orbital period. You get its size, its radius, because the depth of the transit depends on how much of the star's disk the planet covers. Combine that with radial velocity measurements and you can calculate the planet's mass. Mass and radius together give you density, and density tells you what the planet is made of. A density close to that of rock suggests a rocky planet. A density close to that of water suggests a world with a thick atmosphere or an icy composition. A very low density suggests a gas giant, a planet with no solid surface at all, just layers of gas extending down to a liquid or metallic core. The transit method does not just find planets, it characterizes them. And then there is direct imaging. This is the hardest method by far. You point a telescope at a star and try to take a picture of the planet next to it. The problem is the glare. The star is millions or billions of times brighter than the planet. It is like trying to photograph a moth sitting next to a spotlight. The light from the spotlight washes out everything else. To make direct imaging work, you need to block the star's light. Coronagraphs do this, devices that mask the star, creating an artificial eclipse so you can see what is hiding next to it. Even with a coronagraph, direct imaging is incredibly difficult. It works best on young planets, planets that are still hot from their formation and glowing in infrared light. And it works best on planets that orbit far from their stars, where the angular separation is large enough to resolve. Direct imaging has found a few dozen planets, not thousands, a few dozen. But the ones it finds are unique. You are capturing light from the planet itself, not inferring its presence from indirect effects. You can study the planet's atmosphere directly, measure its temperature, its composition, its weather. Direct imaging is rare, but when it works, it is extraordinary. The European Southern Observatory, ESO, notes that imaging an Earth twin, a planet the size and temperature of Earth orbiting a Sun-like star, requires a contrast of about 10 to the negative 9th power, or better at very small angular separation from the star. 10 to the negative 9th. That is 1 part in a billion, blocking out 1 billion times more light from the star than the planet emits. No current telescope can do that. Not reliably. Not yet. Future missions, like the proposed Habitable Worlds Observatory, are being designed with that goal in mind. But for now, direct imaging is limited to large, young, hot planets far from their stars, not the kind of places you would expect to find life. So we have the tools: radial velocity, transits, direct imaging. Each method has its strengths and its blind spots. Together they have revealed a universe full of planets. More planets than stars, probably. Current estimates suggest that nearly every star in the Milky Way has at least one planet. The galaxy contains somewhere between 100 billion and 400 billion stars. That means hundreds of billions of planets, at a minimum. Some stars have multiple planets. Some have none. But on average, planets are everywhere. That is the first big discovery. Planets are not rare, they are the norm. The second big discovery is that planetary systems are weird. Our solar system, the one we grew up with, the one that seemed normal because it was all we knew, turns out to be unusual. We have small rocky planets close to the Sun and large gas giants farther out. That arrangement made sense. It fit the models. Gas giants form where it is cold. Rocky planets form where it is warm. Simple. Except most exoplanetary systems do not look like that. Many of them have gas giants in close orbits, hot Jupiters screaming around their stars in a matter of days. Many of them have planets in the gap between Earth and Neptune, planets we do not have in our solar system. Super-Earths and mini-Neptunes. These are some of the most common types of exoplanets, and we have no examples of them at home. Super-Earths are rocky planets larger than Earth but smaller than Neptune. Masses somewhere between 1 and 10 times Earth's mass. Mini-Neptunes are slightly larger, with thick atmospheres of hydrogen and helium, but still smaller than Neptune itself. Both types are abundant. Kepler found them everywhere, and we have no idea what they are really like because we cannot study one up close. Are super-Earths scaled-up versions of Earth, with thicker crusts and stronger gravity? Or are they something else? Worlds with entirely different geology, different atmospheres, different chemistry? We do not know. Are mini-Neptunes small gas giants, or large rocky planets with runaway atmospheres? Again, we do not know. These planets are common in the galaxy, and they are completely absent from our solar system. That tells us something important. The solar system is not a template. It is one example among many. Planetary systems are diverse. The rules that shaped our neighbourhood do not necessarily apply everywhere else. Then there are the extremes. Rogue planets. Planets that do not orbit any star. They were ejected from their birth systems, flung out into interstellar space by gravitational interactions with other planets, or by close encounters with passing stars. Rogue planets drift through the galaxy alone, untethered, receiving no light from a sun. They are cold, dark, undetectable by most methods because there is no star to wobble, no star to transit, no star to outshine. The only way to find them is through gravitational microlensing, a technique that detects the brief brightening of a background star as a rogue planet passes in front of it, bending the starlight with its gravity. Microlensing surveys have found a handful of rogue planets. Estimates suggest there could be billions of them drifting through the Milky Way, maybe more rogue planets than stars. Most of them will never be detected. They are ghosts, invisible, wandering through the void. Then there are the lava worlds, planets orbiting so close to their stars that their surfaces are molten, dayside temperatures high enough to vaporize rock. These are not habitable in any conventional sense, but they exist. Kepler found dozens of them. One example is Kepler 452b, a rocky planet orbiting its star every 20 hours. 20 hours! The surface is likely a sea of molten lava, constantly churned by the star's gravity. The night side, if it is cool enough, might have a thin crust of solidified rock. But the day side is liquid, a planet-wide ocean of lava, waves of molten rock driven by tidal forces. It is one of the most hostile environments imaginable, and it is real. And then there are the diamond planets. This is where things get speculative. Some planets are thought to be rich in carbon rather than oxygen. In Earth's mantle, carbon mostly bonds with oxygen to form carbonates. But in a carbon-rich environment with less oxygen available, carbon can bond with itself under extreme pressure, forming diamond. Some models suggest that planets orbiting certain types of stars, stars with unusual chemical compositions, could have interiors packed with diamond, layers of crystallized carbon beneath a thin rocky crust. These planets have not been confirmed. The evidence is indirect, based on the chemical makeup of the host stars and models of planetary interiors. But if they exist, they represent yet another flavour of world we never anticipated. A planet where the geology is dominated not by silicates, but by carbon. A diamond world. Why do these extremes matter? Because they expand the range of environments that might support life, or they force us to rethink what habitable means. For decades, the search for life beyond Earth has been guided by a simple rule: follow the water. Life as we know it requires liquid water. Every organism on Earth, from bacteria to blue whales, needs water to function. Water is the solvent in which biochemistry happens. So the obvious strategy is to look for planets where liquid water can exist on the surface. That region around a star is called the habitable zone. Not too close, where water would boil away, not too far where it would freeze, just right. The Goldilocks zone. For a sun-like star, the habitable zone sits roughly where Earth is, give or take. For a cooler star, the zone is closer in. For a hotter star, farther out. The habitable zone is not a guarantee of life. It is just a starting point. A place where the conditions might, in principle, allow liquid water to exist. But the habitable zone concept has limitations. It assumes life needs surface water. It assumes the planet has an atmosphere. It assumes the planet is rocky. All of those assumptions are based on Earth, and Earth is one data point, one example. Astrobiology, the study of life in the universe, has had to broaden its thinking. Because life on Earth exists in places we once thought were uninhabitable. Extremophiles, organisms that thrive in conditions that would kill most other life forms. Bacteria that live in boiling water near hydrothermal vents. Microbes that survive in the freezing deserts of Antarctica. Organisms that tolerate high radiation, extreme acidity, crushing pressure, near vacuum conditions. Life on Earth is tougher, more adaptable, more resilient than we once thought. If life can survive in those conditions on Earth, maybe it can survive in similar conditions elsewhere. Maybe the habitable zone is not a narrow ring around a star. Maybe it is much wider. Maybe it includes environments we have not even considered yet. Europa, one of Jupiter's moons, has a global ocean beneath an ice shell. The surface is frozen solid, but below there is liquid water, heated by tidal forces, possibly in contact with a rocky seafloor, possibly hosting hydrothermal vents. Europa is outside the habitable zone by the traditional definition. It is too far from the Sun, but it has liquid water, it has energy, it has chemistry, it might have life. The same goes for Enceladus, a moon of Saturn, geysers erupting from its south pole fed by a subsurface ocean, shooting water vapor and organic molecules into space. Enceladus is even farther from the Sun than Europa, and yet it is one of the most promising places in the solar system to search for life. The habitable zone as originally defined did not account for moons, it did not account for subsurface oceans, it was too narrow. Astrobiology has expanded the concept. Habitable does not mean Earth-like, it means conditions where life in some form could potentially exist. And then there is the possibility that life does not even need the same chemistry we use. Life on Earth is carbon-based. Every organism we know about is built from carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. Carbon is the backbone. It forms long chains, complex molecules, the kinds of structures that can store information and catalyze reactions. Carbon chemistry is versatile, but it is not the only option. Silicon, the element directly below carbon on the periodic table, can form some of the same kinds of bonds. Silicon-based life has been proposed as a theoretical possibility. It would not look like anything we are familiar with. Silicon bonds are weaker than carbon bonds at high temperatures. Silicon dioxide, the most common silicon compound, is a solid at room temperature. Sand, glass. Not exactly a good medium for biochemistry. But in a different environment, maybe colder, maybe with different solvents, silicon-based life might be possible. Nobody has found any evidence for it, but the fact that we can imagine it, the fact that the chemistry allows for it in principle, means we cannot rule it out. The same goes for other exotic possibilities. Life that uses ammonia as a solvent instead of water. Life that thrives at temperatures far below freezing. Life that does not need a planet at all, drifting through the upper atmospheres of gas giants, or floating in interstellar clouds. These ideas are speculative. Most of them are probably wrong, but the point is that life beyond Earth may not look like life on Earth. It may not use the same chemistry. It may not need the same conditions. The universe is vast. Chemistry is universal. The same elements exist everywhere. The same physical laws apply. If life arose on Earth, it is reasonable to think it could arise elsewhere. And if it did, it might be stranger, more diverse, more adaptable than anything we have imagined. 6,324 confirmed exoplanets. That is the count as of mid-2026. The number is climbing every year. TESS, the Transiting Exoplanet Survey satellite, is scanning the entire sky, looking for transits around the brightest nearby stars. Future missions are being planned. The James Webb Space Telescope is beginning to study the atmospheres of exoplanets, looking for gases that might indicate biological activity. Oxygen, methane, combinations of gases that do not make sense unless something is actively producing them. Webb cannot image an Earth twin, not yet, but it can study larger planets, hot Jupiters, mini Neptunes, super-Earths, anything with a thick enough atmosphere to leave a detectable signature. And what it finds will shape the next generation of missions. If Webb detects biosignatures, gases that are hard to explain without life, the hunt will intensify. Future telescopes will be built specifically to image Earth-sized planets in the habitable zones of nearby stars, to take pictures of them, to study their atmospheres, to search for signs of life. And if we find nothing, if every planet we study turns out to be sterile, that would be a result too. A strange one, an uncomfortable one. The universe is full of planets, hundreds of billions of them in our galaxy alone. Trillions across the observable universe. If none of them have life, if Earth is the only place where chemistry became biology, that raises a different set of questions. Why? What is special about Earth? What conditions are so rare, so specific, that they only occurred once in trillions of chances? Or maybe life is common, but intelligent life is not. Maybe the galaxy is full of microbes, but we are the only species to build telescopes. That would be lonely in a different way. Not alone, exactly, but isolated. The only ones asking the questions. For now, the silence continues. We have not found life beyond Earth. Not yet. We have found the places where it could exist. Planets in habitable zones, moons with subsurface oceans. Environments that, on paper, look promising. But looking promising is not the same as being inhabited. The search continues. Tess is watching the sky. Webb is analysing atmospheres. Future missions are being planned. The technology is improving. The catalogue of known exoplanets is growing. And every new planet, every new data point refines the picture. We are learning what is possible, what is common, what is rare. We are mapping the diversity of worlds in the galaxy. And in doing so, we are learning what it means for a planet to be habitable, what it means for a planet to support life, and what it means for us to be here, asking these questions, in a universe that so far has not answered. The next step outward takes us beyond individual planets, beyond individual stars, beyond even individual galaxies. Because galaxies are not scattered randomly through space. They cluster. They form structures, filaments, walls, voids. The universe on the larger scales is not uniform. It has a shape, a pattern, the cosmic web, and that web is expanding, not just growing, accelerating. Driven by something we do not understand, dark energy. But before we get to what is pushing the universe apart, we need to talk about how we know it is expanding at all. And that story starts with the discovery that nobody wanted to believe. In the early 1920s, most astronomers thought the universe was static, eternal, unchanging. The Milky Way was the universe. Everything we could see belonged to our galaxy. The fuzzy spiral nebulae scattered across the sky were thought to be clouds of gas within the Milky Way, not separate galaxies. The idea that the universe could be expanding, that galaxies could be flying apart from each other, that the cosmos had a history and possibly a beginning, was not on the table. It was not even considered seriously. The universe just was. It had always been there. It would always be there, static, peaceful, permanent. Then Edwin Hubble ruined everything. Working at the Mount Wilson Observatory in California in 1923, Hubble was studying those fuzzy spiral nebulae with the most powerful telescope available at the time, the 100-inch Hooker telescope. He was looking for variable stars, stars whose brightness changes over time. He found them. Specifically, he found Cepheid variables, stars whose brightness pulses on a regular schedule. Cepheids are useful because the period of their pulsation is directly related to their intrinsic brightness. Measure the period, calculate the true brightness, compare it to how bright the star looks from Earth, and you have a distance. Hubble did the math. The Cepheids he was observing in the Andromeda Nebula were so far away that Andromeda could not possibly be part of the Milky Way. It was a separate galaxy, an entire galaxy, sitting more than 2 million light-years away. The universe was vastly larger than anyone had thought. That was the first shock. The second came a few years later. Hubble started measuring the distances to other galaxies and their velocities. The velocity part came from spectroscopy. When you split the light from a galaxy into its component wavelengths, you see absorption lines, dark bands where specific elements in the galaxy's stars have absorbed light. Those lines should appear at specific wavelengths, but they do not. They are shifted. For most galaxies, the lines are shifted toward the red end of the spectrum, redshift. The further away the galaxy is, the more its light is redshifted, and a redshift means the galaxy is moving away from us. In 1929, Hubble published a paper showing that the farther away a galaxy is, the faster it is receding. The relationship is linear. Double the distance, double the velocity. This is Hubble's law. The implication was immediate and unavoidable. If every galaxy is moving away from us, and the farther away they are, the faster they are moving, then the universe is expanding. Not expanding into something, just expanding. The space between galaxies is growing. Galaxies are not flying through space like rockets. Space itself is stretching, carrying the galaxies along with it. Think of it like dots on the surface of a balloon. As you inflate the balloon, The dots move apart, not because they are moving across the surface, but because the surface itself is expanding. From the perspective of any dot, all the other dots are moving away. And the farther away a dot is, the faster it seems to be receding. That is what Hubble saw. That is what the redshift means. The universe is not static. It has never been static. It is expanding. It has been expanding for a very long time, and if it is expanding now, that means it was smaller in the past. Rewind far enough, and everything was closer together. Rewind all the way, and you reach a point where everything, all the matter and energy in the universe, was compressed into an incredibly small, incredibly hot, incredibly dense state. That is the Big Bang. The term Big Bang was actually coined by Fred Hoyle, a physicist who did not believe the theory. He used it mockingly during a radio broadcast in 1949. The name stuck anyway, and the evidence kept piling up. Hubble's redshift observations were the first piece. The second piece came in 1964, completely by accident. Two radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn antenna at Bell Labs in New Jersey. They were trying to calibrate the antenna for satellite communications. They kept picking up noise, a faint hiss coming from every direction in the sky. They thought it was interference. They checked the equipment. They cleaned out pigeon droppings that had accumulated inside the antenna. The noise did not go away. It was coming from space, and it was the same in every direction. A uniform glow of microwave radiation filling the entire sky. What Penzias and Wilson had found was the cosmic microwave background, the CMB. This is light from the early universe. Roughly 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and form neutral hydrogen. Before that moment, the universe was opaque. Photons could not travel far without scattering off free electrons. After that moment, the universe became transparent. Light could travel freely. The photons released at that moment have been travelling through space ever since, and as the universe expanded, those photons were stretched, their wavelengths lengthened, shifting from visible light into the microwave range. The CMB is the afterglow of the Big Bang. It is the oldest light in the universe, and it is everywhere. The temperature of the CMB is about 2.7 Kelvin, just a few degrees above absolute zero. It is faint, but it is detectable, and it is one of the most important pieces of evidence we have for the Big Bang. Penzias and Wilson won the Nobel Prize for the discovery. The third piece of evidence is the abundance of light elements. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur. Protons and neutrons smashed together, forming helium, deuterium, a bit of lithium. The process is called Big Bang nucleosynthesis. The proportions of these elements depend on the conditions in the early universe, the temperature, the density, the expansion rate. Predictions from Big Bang nucleosynthesis match the observed abundances of light elements throughout the universe almost perfectly. Roughly 75% hydrogen, 25% helium by mass, with trace amounts of deuterium and lithium. Exactly what the theory predicts. Stars also produce helium through fusion, but they cannot account for all the helium we see. The only way to explain the observed abundances is if the universe went through a hot, dense phase early on. Big Bang nucleosynthesis, another confirmation. So the universe is expanding. It started from a hot, dense state. The CMB is real. The light element abundances match predictions. The Big Bang theory is not speculation. It is the framework that fits the observations. And once you accept that the universe is expanding, you have to ask what the expansion looks like on the larger scales. Because galaxies are not evenly distributed, they cluster. And those clusters form larger structures, superclusters, filaments, walls. And between those structures there are voids, enormous empty regions where almost no galaxies exist. Map the positions of galaxies across billions of light years and a pattern emerges. Galaxies are arranged in a web-like structure. Long filaments of galaxies stretching across hundreds of millions of light years, connected at nodes where galaxy clusters sit. Between the filaments, vast voids, regions where galaxies are scarce. The structure looks organic. It looks like a sponge, or a neural network, or the scaffolding of some immense invisible architecture. This is the cosmic web. It is the largest known structure in the universe, and it formed through gravity. In the early universe, matter was distributed almost uniformly. Almost. There were tiny fluctuations in density, small regions where matter was slightly more concentrated than average. Gravity amplified those fluctuations. Denser regions pulled in more matter, becoming denser still. Over billions of years, those small differences grew into the structures we see today. Filaments formed along the densest regions. Voids formed where matter was pulled away. The cosmic web is a direct consequence of gravity acting on an expanding universe over immense timescales. One of the best visualizations of the cosmic web comes from large galaxy surveys. The Sloan Digital Sky Survey, for example, mapped the positions of millions of galaxies. Plot them in 3 dimensions and the web becomes visible. Long chains of galaxies, clusters at the intersections, voids in between. The structure is fractal-like, repeating at different scales. Small groups of galaxies cluster together. Those groups cluster into larger structures. Those structures connect into filaments. The filaments form a network spanning billions of light years, and all of it is held together by gravity. The cosmic web is not a fixed structure. It is dynamic. Galaxies are moving along the filaments, pulled by the gravity of nearby clusters. The web is evolving, growing denser in some regions, more diffuse in others. The universe is not just expanding, it is organizing itself. But there is a problem. The cosmic web exists. That is not in question. The problem is that it formed too fast. Run the numbers on how quickly structure should have grown in an expanding universe, starting from the tiny density fluctuations we see in the cosmic microwave background, and the timescale does not work. The universe is roughly 14 billion years old. The CMB shows fluctuations on the order of 1 part in 100,000. Those fluctuations are the seeds of structure. Gravity pulls on those seeds, amplifying them over time, but the amplification is slow. Start with fluctuations that's small, and you do not get the cosmic web we see today in only 14 billion years. Not unless something happened early on to boost the size of those fluctuations. That something is called inflation. Inflation is an idea that sounds absurd until you realize it solves 3 major problems at once. The theory, proposed by Alan Guth and others in the early 1980s, suggests that the universe went through a brief period of exponential expansion in the first fraction of a second after the Big Bang. Exponential means the expansion doubled repeatedly over incredibly short timescales. The numbers are staggering. In roughly 10 to the negative 35 seconds, the universe expanded by a factor of about e to the 60. That is 10 to the 26. A billion times larger in an instant. The expansion was faster than light. Not because anything moved faster than light, but because space itself was expanding. Light speed is a limit on how fast things can move through space. It does not limit how fast space itself can expand. Why would the universe do that? What drove inflation? The best current models suggest it was driven by a scalar field, a hypothetical energy field that permeated all of space in the early universe. This field had a very high energy density, and that energy drove the exponential expansion. Eventually the field decayed, the energy was converted into particles and radiation, and the universe transitioned into the more familiar, slower expansion we see today. The details are still being worked out. Inflation is not a confirmed theory in the way the Big Bang is, but it solves problems that no other idea has managed to solve. Problem 1, the horizon problem. The cosmic microwave background has almost exactly the same temperature in every direction. Variations are tiny, 1 part in 100,000. That uniformity is strange because regions of the CMB on opposite sides of the sky are too far apart to have ever been in contact. Light has not had enough time to travel between them since the Big Bang. So how did they end up at the same temperature? In standard Big Bang cosmology, there is no good answer. Inflation solves it. If the universe underwent exponential expansion early on, regions that are now widely separated were once close together, in thermal contact. Inflation stretched them apart. The uniform temperature is not a coincidence. It is a relic of a time when those regions were near each other. Problem 2, the flatness problem. The geometry of the universe depends on its density. If the density is high, the universe curves back on itself like the surface of a sphere. If the density is low, the universe curves outward, like a saddle. If the density is exactly right, the universe is flat, like a sheet of paper. Observations suggest the universe is very close to flat, remarkably close, but flatness is an unstable state. Any deviation from flatness in the early universe gets amplified over time. For the universe to be as flat as it is today, it would have had to start out flat to an absurd degree of precision. 1 part in 10 to the 60 or more. That is not impossible, but it is deeply unlikely. Inflation solves it. Exponential expansion smooths out curvature. Even if the universe started with significant curvature, inflation stretched it flat. A curved surface looks flat if you zoom in close enough. Inflate a balloon to the size of the observable universe, and any patch of it looks perfectly flat. Problem 3. The structure problem. The tiny fluctuations in the CMB, the seeds of the cosmic web, need to have started somewhere. In standard Big Bang cosmology, those fluctuations are just there, unexplained initial conditions. Inflation provides a mechanism. Quantum fluctuations in the inflating field get stretched to cosmic scales during inflation. Those quantum ripples become the density fluctuations that eventually grow into galaxies and clusters. Inflation turns quantum noise into the large-scale structure of the universe. That is elegant. It connects the very small to the very large, and it makes predictions that can be tested. The pattern of fluctuations in the CMB, the way they vary across different scales, matches what inflation predicts. Not perfectly. There are details still being debated. But the broad agreement is striking. If inflation happened, it happened in the first moments after the Big Bang. The universe expanded from something unimaginably small to something roughly the size of a grapefruit in about 10 to the negative 35 seconds. Then inflation ended. The energy driving the expansion decayed into particles and radiation. The universe was hot, dense, filled with a soup of fundamental particles. It continued expanding, but at a much slower rate. Protons and neutrons formed, nuclei formed, atoms formed. Light travelled freely for the first time, the CMB was released, gravity pulled matter together, the first stars ignited, galaxies assembled, the cosmic web emerged, and here we are, 14 billion years later, looking back at the light from that early universe, trying to piece together what happened. The expansion has not stopped. It has been running since the Big Bang. For most of the universe's history, the expansion was slowing down. Gravity pulls everything together. You would expect gravity to slow the expansion, maybe even reverse it eventually, pulling the universe back into a collapse. That was the assumption. The universe is either expanding forever, slowly coasting to a stop, or it is expanding now but will eventually reverse into a big crunch, a hot, dense end state mirroring the Big Bang. Which scenario plays out depends on the density of the universe. If there is enough matter, gravity wins, the universe collapses. If there is not enough matter, expansion wins, the universe expands forever. Astronomers spent decades trying to measure the density of the universe, trying to figure out which fate awaited us. Then, in 1998, 2 independent teams studying distant supernovae discovered something no one expected. The expansion is not slowing down, it is speeding up. The universe is accelerating. That should not be possible. Gravity pulls, it does not push. But the observations were clear. Distant supernovae were dimmer than they should be, which means they're farther away than expected. The universe expanded more than it should have during the time the light was travelling toward us. Something is pushing the expansion faster. That something is called dark energy. We will get to what dark energy might be in the next chapter. For now, the point is that the discovery changed everything. The expansion is accelerating. The universe is not coasting to a stop. It is not collapsing. It is speeding up. That changes the story of the universe's fate. If the expansion keeps accelerating, driven by dark energy, the universe will continue to grow colder, darker, more dilute. Galaxies will drift farther apart. Eventually, distant galaxies will recede so fast that their light can no longer reach us. The observable universe will shrink. The Milky Way and the Andromeda merger remnant will be alone, surrounded by darkness. Stars will exhaust their fuel. No new stars will form because the gas will have been used up. The universe will be filled with dead stars, black holes, and the faint glow of particles decaying over timescales longer than the current age of the cosmos. This is the Big Freeze, also called heat death. The universe does not end in a dramatic collapse. It fades, slowly, over trillions of years. Heat dissipates, energy spreads out, everything approaches the same cold, uniform temperature. The universe becomes a vast, dark, empty expanse where nothing happens anymore. That is the leading scenario based on current observations, but there are alternatives. If dark energy does not stay constant, if it strengthens over time, the acceleration could get worse, much worse. Space itself could start ripping apart structures that are currently held together by gravity. First, galaxy clusters would be torn apart, then galaxies, then solar systems, then planets, then atoms. Even the particles inside atoms could be torn apart as space expands faster than the forces holding them together. This is the big rip. It is speculative. It depends on dark energy behaving in a way we have not observed. But it is possible. The universe could end not with a whimper, but with a violent tearing of the fabric of spacetime itself. And if dark energy somehow reverses, if the expansion slows and then collapses, we get the big crunch. The universe contracts, galaxies collide, space gets denser, hotter. The cosmic microwave background shifts from microwaves back into visible light, then ultraviolet, then X-rays. The universe heats up. Eventually, everything is compressed into a hot, dense state similar to the Big Bang. Does the universe bounce? Does it collapse into a singularity and stop? Does another cycle begin? We do not know. The Big Crunch is not favoured by current data, but it is not ruled out completely. The most likely fate, the one that fits the observations, is the Big Freeze. Continued expansion, accelerating expansion. A universe that grows colder, darker, emptier over timescales so long they are hard to conceptualize. Trillions of years from now, the last stars will burn out. The universe will be populated by black holes and the faint remnants of dead galaxies. Even black holes eventually evaporate through Hawking radiation, a process that takes 10 to the 100 years or more. After that, nothing but a thin soup of particles drifting through an ever-expanding void. No light, no heat, no structure. Just an infinite, cold, empty universe coasting toward a state of maximum entropy. That is the end. Not a bang. A fade. It is unsettling. The universe is not eternal in any meaningful sense. It had a beginning. It will have an end. Not an end where everything stops, but an end where everything becomes so diluted, so spread out, that nothing interesting can happen anymore. The stars we see tonight, the galaxies in Hubble images, the cosmic web stretching across billions of light years, all of it is temporary. The universe is dynamic, it is evolving, and its evolution is heading toward a state where the lights go out and nothing replaces them. But that is trillions of years away. For now, the universe is still vibrant. Stars are forming, galaxies are colliding, black holes are feeding. The cosmic web is growing denser in some regions, more diffuse in others. We are living in the middle of the story, not the end. And that middle is shaped by forces we can see and forces we cannot. Gravity pulls matter together, building the cosmic web. Dark energy pushes the universe apart, accelerating the expansion. And there is something else, something invisible, something that makes up most of the mass in the universe, and yet emits no light. Dark matter. It does not interact with light. It does not collide with normal matter in ways we can easily detect. But it is there. We know it is there because of how galaxies rotate, how galaxy clusters move, how light bends around massive objects. Dark matter is everywhere. And it shapes the universe just as much as the matter we can see. Maybe more. The cosmic web exists because of dark matter. The galaxies we see are sitting inside invisible halos of dark matter, held together by gravity from material we cannot observe directly. The universe is not just made of stars and gas and planets. It is made mostly of things we cannot see. Dark matter, dark energy. The invisible architects of the cosmos, and that is where the story goes next. The cosmic web exists because of dark matter. That is not speculation. That is not a theoretical nicety you can ignore if you're uncomfortable with invisible things. The structure we just walked through, the filaments of galaxies stretching across hundreds of millions of light years, the voids between them, the way galaxy clusters sit at the intersections like cities at highway junctions, none of that would exist without dark matter. And yet we have never seen it directly. Not once. We know it is there because of what it does. Because galaxies spin in ways that make no sense unless something invisible is holding them together. Because light bends around galaxy clusters by amounts too large to explain with the visible matter alone. Because the cosmic microwave background shows patterns that only make sense if dark matter was already pulling normal matter into clumps when the universe was less than 400,000 years old. The evidence is overwhelming. The problem is that we have no idea what dark matter is. Let's start with the first clue: galaxy rotation curves. In the 1930s, an astronomer named Fritz Zwicky was studying the Coma cluster, a large collection of galaxies about 300 million light-years away. He measured how fast individual galaxies within the cluster were moving. The galaxies were orbiting the cluster's centre of mass, held together by their mutual gravity. Zwicky used the velocities to calculate how much mass the cluster must contain. The number he got was enormous, far larger than the mass of all the visible stars and gas in all the galaxies in the cluster. There was not enough visible matter to hold the cluster together. The galaxies were moving too fast. They should have been flying apart, but they were not. Zwicky concluded that the cluster must contain a large amount of unsichtbar materie, invisible matter, dark matter. The name stuck. The observation was largely ignored for decades. The second clue came in the 1970s. Vera Rubin, working at the Carnegie Institution, was studying the rotation of spiral galaxies. Specifically, she was measuring how fast stars orbit the galactic centre at different distances. The expectation was simple. Most of a galaxy's visible mass is concentrated near the centre. Stars close to the centre should orbit faster because they feel stronger gravity. Stars farther out should orbit slower, the same way planets farther from the Sun take longer to complete an orbit. That is basic Newtonian mechanics. The inner planets move fast, the outer planets move slow. Galaxies should behave the same way, except they do not. Rubin found that stars in the outer regions of spiral galaxies orbit just as fast as stars closer to the centre. The rotation curve, a plot of orbital speed versus distance from the centre, stays flat instead of dropping off. That should not happen. Not unless there is more mass farther out than we can see, a lot more mass, spread out in a halo around the visible galaxy, mass that does not emit light, dark matter. The same pattern shows up in galaxy after galaxy. Nearly every spiral galaxy we have measured has a flat rotation curve. The stars are orbiting too fast to be held in by the gravity of the visible matter alone. The only explanation that fits is that each galaxy is embedded in a much larger halo of dark matter. The visible galaxy, the disk of stars and gas we see in photographs, is just the tip of the iceberg. The dark matter halo extends far beyond the visible edge, sometimes stretching out 10 times farther than the stars. Most of the mass in a galaxy is not in the stars, it is in the dark matter. We live inside a cloud of invisible material. The Milky Way is not a disk of stars, it is a disk of stars sitting inside a vast spherical halo of something we cannot see. Our solar system is moving through that halo right now. Dark matter is streaming past the Earth at this very moment. We do not feel it, we do not see it, but it is there. The third clue comes from gravitational lensing. Einstein's theory of general relativity predicts that mass bends spacetime. Light travelling through curved spacetime follows a curved path. If a massive object, like a galaxy cluster, sits between us and a more distant galaxy, the light from the distant galaxy gets bent as it passes near the cluster. The result is that we see multiple distorted images of the distant galaxy, arcs and rings smeared around the cluster. The degree of bending depends on the mass of the cluster. More mass means more bending. Astronomers can measure the lensing and calculate how much mass is required to produce the observed distortions. And once again, the numbers do not add up. The lensing is stronger than it should be based on the visible matter alone. Galaxy clusters contain far more mass than we can see. The extra mass is dark matter. In some cases, the dark matter outweighs the visible matter by factors of 10 or more. The most famous example is the Bullet cluster. Two galaxy clusters collided at high speed. During the collision, the galaxies passed through each other mostly unaffected because space between stars is vast. But the hot gas that fills the space between galaxies in a cluster did collide. Gas clouds slammed into each other, slowed down, and piled up in the middle of the collision zone. Astronomers can see that gas because it is hot enough to glow in X-rays. So after the collision, most of the visible matter is in the centre. But when astronomers mapped the gravitational lensing, they found that most of the mass is not in the centre. It is in two clumps on either side of the collision zone moving with the galaxies. The dark matter did not collide. It passed straight through, just like the galaxies. The bullet cluster is direct evidence that dark matter is real, that it is separate from normal matter, and that it interacts through gravity but not through electromagnetic forces. It does not emit light. It does not absorb light. It does not collide with itself in ways that generate heat or slow it down. It is dark in every sense of the word. The fourth clue comes from the cosmic microwave background and the formation of structure. In the early universe, matter was distributed almost uniformly. Tiny fluctuations existed, density variations of about 1 part in 100,000. Those fluctuations are visible in the CMB as slight variations in temperature across the sky. Gravity amplified those fluctuations over billions of years, pulling matter into the denser regions and creating the cosmic web. But there is a problem. Normal matter, baryons, interacts with light. In the early universe, photons and baryons were tightly coupled. Radiation pressure pushed back against gravity, slowing the growth of structure. If the universe contained only normal matter, the tiny fluctuations in the CMB would not have had enough time to grow into the large-scale structures we see today. The math does not work. The universe is only about 14 billion years old. That is not enough time for normal matter alone to assemble into galaxies and clusters starting from fluctuations that small, unless something else was already pulling normal matter together. Dark matter does not interact with light. It does not feel radiation pressure. Dark matter started collapsing into clumps long before normal matter could. By the time the CMB was released and normal matter decoupled from radiation, dark matter had already built the scaffolding. Normal matter fell into the gravitational wells created by dark matter, forming the first stars and galaxies inside dark matter halos. The cosmic web exists because dark matter built the framework first. Observations of cosmic structure formation only make sense if dark matter is real, and if it makes up most of the matter in the universe. Put all the evidence together and the conclusion is unavoidable. Dark matter exists. It outweighs normal matter by a factor of about 5 to 1. Roughly 85% of the matter in the universe is dark matter. Only 15% is the stuff we can see. Stars, gas, planets, people, all of it is the minority component. The universe is dominated by something we cannot observe directly. That raises an obvious question. What is it? What is dark matter made of? The honest answer is that we do not know. We have ideas. We have candidates. But after decades of searching, we have not detected dark matter particles directly. Not once. And that is deeply frustrating because the evidence for dark matter is ironclad. It is there. We know it is there. We can map where it is. We can measure its effects. We just cannot catch it. The leading candidate for decades has been WIMPs, weakly interacting massive particles. The name is unfortunate but accurate. WIMPs are hypothetical particles that interact through gravity and the weak nuclear force, but not through electromagnetism. That would explain why they do not emit or absorb light. The weak force is short range, so WIMPs would pass through normal matter almost unhindered. They would be invisible, undetectable except through gravity. WIMPs fit naturally into extensions of the standard model of particle physics. Theories like supersymmetry predict particles with exactly the properties WIMPs need, and the math works out nicely. If WIMPs exist with the predicted masses and interaction rates, they would have been produced in the right abundance in the early universe to account for all the dark matter we observe. This is called the WIMP miracle. It is not a miracle in the religious sense. It is a coincidence that seems too good to ignore. The predicted properties of WIMPs line up almost perfectly with what dark matter needs to be. So physicists built detectors, enormous, incredibly sensitive experiments buried deep underground to shield them from cosmic rays and other background noise. The idea is simple. If WIMPs exist, they are streaming through the Earth constantly. Occasionally, very rarely, a WIMP might collide with an atomic nucleus in the detector. The collision would produce a tiny flash of light or a tiny vibration. The detectors are designed to catch that signal. Experiments have been running for decades. The detectors have gotten larger, more sensitive, more sophisticated, and they have found nothing. No WIMPs, not a single unambiguous detection. The null results have pushed the allowed parameter space for WIMPs into narrower and narrower corners. Some versions of WIMPs are now ruled out entirely. Others are still possible, but the space where they could hide is shrinking. The WIMP miracle is starting to look less miraculous and more like a coincidence that did not pan out. That leaves other candidates, MACOs, massive compact halo objects. These are not exotic particles. They are ordinary astrophysical objects that do not emit much light. Brown dwarfs, black holes, neutron stars, rogue planets, ancient white dwarfs. Objects made of normal matter, but too small or too cold to see. For a while, MACOs were considered a viable explanation for dark matter. Surveys looked for them using a technique called microlensing. If a MACO passes in front of a distant star, its gravity bends the starlight, causing the star to briefly brighten. Several microlensing surveys ran in the 1990s and early 2000s. They found some MACOs, but not enough. Nowhere near enough to account for all the dark matter. MACOs can explain a small fraction of the missing mass, but they cannot be the whole story. Most dark matter is not made of normal matter. It is something else. Axions are another candidate. These are hypothetical ultralight particles originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force. Axions would be incredibly light, millions or billions of times lighter than an electron. They would interact so weakly with normal matter that detecting them would be extraordinarily difficult. But if they exist, they could be produced in enormous numbers in the early universe, enough to account for all the dark matter. Axion detectors are being built, experiments designed to catch the tiny signals axions might produce in strong magnetic fields. The searches are ongoing. So far, no detections. But the parameter space is huge. Axions could exist across a wide range of masses, and we have only started to explore the possibilities. And then there are the more exotic ideas. Sterile neutrinos, dark photons, hidden sectors of particles that do not interact with the standard model at all except through gravity. Some theories propose that dark matter is not a single particle, but a complex hidden sector with its own forces and interactions, a dark chemistry mirroring the familiar one. The possibilities are vast. The problem is that every candidate so far has either been ruled out or remains undetected. Dark matter is real. The evidence is overwhelming. But identifying what it is made of has turned out to be one of the hardest problems in modern physics. We can see its effects everywhere. We can map it. We can measure its distribution across the universe. We can simulate how it clumps and flows. We just cannot catch it. Not yet. And then there is the other problem, dark energy. If dark matter is frustrating because we cannot detect it, dark energy is frustrating because we cannot even explain why it exists. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. In the late 1990s, two independent teams studying distant supernovae discovered that the universe is not just expanding. It is expanding faster now than it was billions of years ago. That should not happen. Gravity pulls. It slows things down. The expansion of the universe should be decelerating, slowed by the gravitational attraction of all the matter in the universe. Instead, it is speeding up. Something is pushing the universe apart. Something with enough energy to overcome the gravitational pull of all the matter and dark matter combined. That something is dark energy. The observations are solid. Type Ia supernovae are excellent standard candles. They are exploding white dwarfs that reach roughly the same peak brightness every time. Measure the brightness, compare it to how bright the supernova looks from Earth, and you get a distance. Measure the redshift of the host galaxy and you get the recession velocity. Combine distances and velocities for supernovae at different redshifts, and you can map the expansion history of the universe. The results were shocking. Distant supernovae were dimmer than expected. That means they are farther away than they should be. The universe expanded more than it should have during the time the light was travelling toward us. The expansion is accelerating. The discovery earned Saul Perlmutter, Brian Schmidt and Adam Rees the Nobel Prize in Physics in 2011. So what is dark energy? The simplest explanation is the cosmological constant. This is a term Einstein added to his equations of general relativity back in 1917. He included it to keep the universe static, counteracting the pull of gravity. When Hubble discovered the universe was expanding, Einstein called the cosmological constant his biggest blunder. But the constant never actually went away. It's a perfectly valid term in the equations. It represents a constant energy density filling all of space. Empty space, vacuum, has energy. That energy does not dilute as the universe expands. Add more space and you add more vacuum energy. The result is a repulsive force that pushes space apart. The more the universe expands, the stronger the push becomes. The cosmological constant fits the supernova data almost perfectly. It explains the accelerated expansion. It is mathematically simple. It works. The problem is that nobody can explain why the cosmological constant has the value it does. Quantum field theory predicts that empty space should have energy. But when you calculate how much energy, the answer is absurdly large, off by a factor of 10 to the 120. That is not a small error. It is the worst prediction in the history of physics. The observed value of the cosmological constant is tiny compared to what theory predicts. Why? Nobody knows. There is no good explanation for why the vacuum energy is so small, yet still large enough to dominate the expansion of the universe. The cosmological constant works as a description. It does not work as an explanation. It is a fit to the data, not a theory. That has led to alternative ideas. Quintessence is one. Instead of a constant energy density, quintessence treats dark energy as a dynamic field, something that changes over time, a scalar field that fills the universe, with properties that evolve as the universe expands. Quintessence can produce accelerated expansion under the right conditions, and unlike the cosmological constant, the energy density of a quintessence field can vary. That gives the model more flexibility. It can potentially explain why dark energy started to dominate the expansion relatively recently in cosmic history, instead of being constant from the beginning. The challenge is that quintessence models have more free parameters, they are more complicated, and so far observations have not found clear evidence that dark energy is changing over time. The data is consistent with a cosmological constant. Quintessence is still possible, but it is harder to distinguish from a constant than early models hoped. Then there are modified gravity theories. These proposals argue that dark energy is not a real substance. Instead, gravity itself behaves differently on cosmic scales than general relativity predicts. Maybe Einstein's equations need a correction term that only becomes important over distances of billions of light years. Maybe gravity is weaker on large scales, reducing the pull that should slow the expansion. Modified gravity models can reproduce the observed acceleration without invoking a new energy component. The appeal is philosophical. You're not adding something mysterious to the universe. You're tweaking the rules. The problem is that modified gravity theories are hard to test. They have to reproduce all the successes of general relativity on smaller scales, while introducing new behavior on cosmic scales. That is a delicate balancing act. Many modified gravity models have been ruled out by observations, others remain viable. But the distinction between modified gravity and quintessence is not always sharp. Some models blur the line. A review of modified gravity and coupled quintessence noted plainly that the distinction between modified gravity and quintessence, or dynamical dark energy, is difficult. They can look the same observationally, even though the underlying ideas are different. What we do know is that dark energy, whatever it is, makes up about 73% of the total energy content of the universe. Dark matter makes up about 22%. Normal matter, everything made of atoms, stars, planets, gas, dust, people, makes up about 4.4%. Those numbers come from the first-year results of the Wilkinson Microwave Anisotropy Probe, WMAP, published in 2003. Later summaries commonly round the cosmic budget to about 95% dark universe. Dark matter plus dark energy. Only 5% of the universe is made of stuff we understand. 95% is dark, invisible, unknown. That is not a small gap in our knowledge. It is a chasm. We have built a remarkably successful model of cosmology, Lambda CDM. Lambda stands for the cosmological constant. CDM stands for cold dark matter. The model fits a huge range of observations: the cosmic microwave background, large-scale structure, galaxy clustering, baryon acoustic oscillations, the abundance of light elements, supernova distances. It works. But it is built on two components we do not understand: dark matter and dark energy. Together they dominate the universe, and we cannot explain what either one is. Here is what that means. The stars you see at night, the galaxies in telescope images, the planets, the gas clouds, the black holes, all of it is a trace component, a rounding error. The universe is made mostly of things we have never directly detected. We infer their existence from their effects. We can map where dark matter is by watching how it bends light and pulls on galaxies. We can measure dark energy by tracking the expansion history of the universe, but we cannot touch dark matter. We cannot bottle dark energy. We cannot build a detector that captures dark energy the way we can capture photons or electrons. The overwhelming majority of the universe is invisible to us, not because we lack the right instruments, but because the stuff itself does not interact with light or with normal matter in ways that are easy to detect. We live in a universe we cannot see. Nick Kaiser predicted weak-lensing cosmic shear from large-scale structure back in 1987. The idea was that the gravitational influence of dark matter spread across the universe would distort the shapes of distant galaxies in a predictable pattern. Measure that distortion, and you can map the dark matter directly. In 2001, the 2-degree field galaxy redshift survey decisively measured cosmic shear for the first time. The signal was there. Weak lensing became a powerful tool for mapping dark matter. The technique has been refined over the past 2 decades. Surveys like the Dark Energy Survey, DES, are combining weak lensing with galaxy clustering, supernovae, and other probes to measure the properties of dark matter and dark energy with increasing precision. The goal is to find deviations from the simplest models. Hints that dark energy is not a cosmological constant. Evidence for new physics. So far, the data keeps coming back consistent with lambda CDM. The cosmological constant is a perfect fit to the dark energy data, even if we cannot explain it. That is both reassuring and frustrating. The model works, but it leaves the biggest questions unanswered. The origin of dark energy is currently unknown. That is a quote from a dissertation summary on modified gravity and cosmic acceleration. It is blunt. It is honest. We do not know. We have models. We have data. We do not have an explanation. And the same goes for dark matter. We have mapped its distribution. We understand how it shapes structure. We do not know what it is. These are not small gaps. These are foundational questions about the nature of reality. The universe is dominated by components we do not understand. That should bother you. It bothers physicists. It is one of the driving forces behind modern cosmology and particle physics. Find dark matter. Explain dark energy. Those are the grand challenges. Solve them and you rewrite the story of the universe. There is something deeply uncomfortable about living in a universe where 95% of the content is invisible. We have spent centuries learning to trust observations, to demand evidence, to insist that claims be backed by data. And now the data is telling us that most of the universe is made of stuff we cannot observe directly. The evidence is indirect. Galaxy rotation curves, gravitational lensing, structure formation, supernova distances, cosmic microwave background patterns, all of it points to the same conclusion. Dark matter and dark energy are real, but the evidence is gravitational. It is not like detecting a new element in a spectroscope. It is watching how things move and inferring that something invisible must be pulling or pushing. That is harder to accept. It feels less concrete. But the evidence is overwhelming. The strongest evidence for dark matter is indirect. Its gravity shows up in motions, lensing, and structure, not in emitted light. Dark matter has never emitted a photon we could detect, and yet we know it is there because the alternative, that galaxies and clusters behave the way they do without extra mass, violates every law of physics we understand. The same goes for dark energy. The universe is accelerating. That is not speculation. It is observation. The expansion rate is increasing. And the simplest explanation, the one that fits the data, is that empty space has energy. Vacuum energy. The cosmological constant. It sounds absurd. Empty space containing energy that pushes the universe apart. But the math works. The observations match. And so far, no alternative explanation has fit the data as well. We are left with a universe that is mostly invisible and mostly not understood. The visible universe, the stars and galaxies we see, is a tiny island in a sea of darkness. And that sea is not empty. It is full of dark matter and dark energy, shaping the cosmos in ways we're only beginning to map. The search continues. Detectors buried underground are still looking for WIMPs. Experiments are searching for axions. Telescopes are measuring cosmic shear, tracking supernovae, mapping the large-scale structure in ever greater detail. Every new observation refines the picture. Every null result from a dark matter search narrows the possibilities. Slowly we are closing in, or at least we hope we are. It is possible that dark matter is something we have not thought of yet. Something so exotic, so weakly interacting, that we will never detect it directly. It is possible that dark energy is simply the cosmological constant, and there is no deeper explanation. That would be unsatisfying. But the universe is not obligated to satisfy our curiosity. It is what it is. And what it is, as best we can tell, is a cosmos dominated by invisible components we can measure but not explain. That leads to a bigger question. If 95% of the universe is dark, if most of what exists is beyond our ability to directly observe, what else might be out there? What other structures, what other realities, might exist beyond the reach of our instruments? The observable universe has a horizon, a boundary set by the speed of light and the age of the universe. We can only see so far. Beyond that, there is more universe, more space, more galaxies, possibly more structures we will never detect. And some theories suggest that what we call the universe might itself be a small part of something much larger, a multiverse, a collection of universes, each with its own laws, its own constants, its own history. That is the final step outward, beyond the horizon of the observable cosmos, into speculation, into possibility, into the deep questions about why the universe exists at all, and whether what we see is all there is. Let's start with what we can actually see. The observable universe is not the entire universe. That needs to be clear from the beginning because the distinction matters. When astronomers talk about the observable universe, they are talking about the region of space from which light has had enough time to reach us since the Big Bang. The universe is roughly 14 billion years old. Light travels at a finite speed, so in principle, we should only be able to see objects whose light has been travelling for 14 billion years or less. Except the universe has been expanding the entire time that light was travelling, so the objects we see now are much farther away than 14 billion light years. The present-day diameter of the observable universe is about 92 to 93 billion light years, not 14 billion, 93 billion. That is the distance across the region we can, in principle, observe. Not the distance light has travelled, the distance to the objects whose ancient light is reaching us now, accounting for how much the universe has expanded while that light was in transit. That 93 billion light-year figure is not the edge of the universe, it is the edge of what we can see. The boundary is called the particle horizon. It is an observational limit, not a physical edge. There is no wall out there, no barrier, no sign saying you have reached the end of reality. The particle horizon is centered on us. It is our horizon. Every observer in the universe has their own particle horizon, their own observable bubble. An observer in a galaxy 10 billion light-years away has a different observable universe than we do. Their horizon includes regions we cannot see. Our horizon includes regions they cannot see. The observable universe is not a universal concept. It is observer-dependent. What you can see depends on where you are and how long light has had to travel to reach you. Beyond our observable horizon, the universe continues. That much is almost certain. There is no reason to think space just stops at the edge of what we can see. The universe beyond our horizon is probably much like the universe within it. More galaxies, more stars, more planets. More of the same structures we see nearby, stretching out for distances we cannot measure and may never be able to measure. How far does it go? We do not know. The universe might be infinite. It might be finite but unbounded, curved back on itself like the surface of a sphere. We do not have enough information to tell. Observation suggests the universe is very close to flat, which is consistent with it being infinite. But close to flat is not the same as exactly flat. There is still room for curvature. The total universe could be vastly larger than the observable portion and still have a finite size, or it could go on forever. Both options are consistent with current data. We are standing inside something enormous, looking out as far as we can, and we still cannot see the edges. If there are edges, that is unsettling enough. But it gets stranger, because some of the best models we have for how the universe began suggest that what we call the universe, the whole thing, observable and unobservable, might itself be just one bubble in a much larger structure, a multiverse. The idea has been around in various forms for decades, but it gained serious traction in cosmology with the development of inflationary theory. Inflation, the brief period of exponential expansion in the first fraction of a second after the Big Bang, solves several major problems in cosmology. We talked about it earlier. The horizon problem, the flatness problem, the structure problem. Inflation fixes all of them. And the math that makes inflation work also suggests something unexpected. Inflation might not have stopped everywhere at once. Here is the idea. Inflation is driven by a scalar field, an energy field that permeates space. In most regions, the field eventually decays, inflation ends, and the universe transitions into the slower expansion we see today. That is what happened in our region. But the field does not have to decay everywhere at the same time. In some regions, inflation keeps going, and because space is expanding exponentially, those inflating regions grow faster than the regions where inflation has stopped. The result is a fractal structure. Pockets where inflation has ended, bubbles of slower expansion, embedded in a background that is still inflating. Each pocket is a universe. Our observable universe is one such pocket. But there could be others, infinitely many others, constantly being created as new regions undergo the transition from inflation to normal expansion. This is the inflationary multiverse. Each bubble universe in the inflationary multiverse would have its own properties. The low-energy laws of physics, the values of fundamental constants, even the number of dimensions of space, could vary from bubble to bubble. The idea is that during inflation, the scalar field can settle into different configurations, different vacuum states. When it decays, each vacuum state corresponds to a different set of physical laws. In our bubble, the electron has a certain mass, the speed of light has a certain value, gravity has a certain strength. In another bubble, those numbers could be different, drastically different. The laws of physics we observe are not necessarily universal. They are local, specific to our bubble. Other bubbles might have entirely different rules. This connects to string theory, the leading candidate for a unified theory of physics that attempts to reconcile general relativity with quantum mechanics. String theory is not a single theory. It is a family of theories, all built on the idea that the fundamental constituents of reality are not particles but tiny vibrating strings. The way a string vibrates determines what kind of particle it appears to be. An electron is one vibrational mode, a photon is another. The mathematics of string theory requires extra dimensions of space beyond the 3 we experience. Most versions of string theory require 10 dimensions of space, plus time. The extra dimensions are thought to be compactified, curled up so small that we cannot detect them. But the way those extra dimensions are curled up affects the physics we observe in the remaining 3 large dimensions. Different configurations of the extra dimensions lead to different effective laws of physics. The number of possible configurations is staggering. Early estimates suggested thousands of possibilities. Later analyses pushed the number higher, much higher. Recent discussions cite a landscape on the order of 10 to the 500th power possible configurations, 10 to the 500th. That is not a number you can visualize. It is not a number you can count to. It is larger than the number of atoms in the observable universe by a factor so enormous that the comparison is meaningless. The string theory landscape is a space of possibilities, each one corresponding to a different vacuum state, a different way the extra dimensions could be arranged, a different set of physical laws, and the inflationary multiverse provides a mechanism for exploring that landscape. As inflation creates new bubble universes, the scalar field can decay into different vacuum states in different bubbles. The multiverse does not just contain many universes, it contains many kinds of universes, each one realizing a different point in the string theory landscape. This is speculative. That needs to be said plainly. The inflationary multiverse is a theoretical possibility, not an established fact. String theory is a framework, not a confirmed description of reality. The landscape is a mathematical structure, not an observed catalogue of universes. We have no direct evidence that other bubble universes exist. We cannot see them. We cannot visit them. We cannot communicate with them. If another bubble exists beyond our cosmic horizon, its light will never reach us. The space between bubbles is expanding faster than light, driven by the ongoing inflation in the background. We are causally isolated, stuck in our bubble, unable to confirm or rule out the existence of others. That makes the multiverse hypothesis difficult to test, and that makes some physicists uncomfortable. Science is supposed to be about testable predictions, falsifiable claims, experiments that can confirm or refute a theory. The multiverse, as currently formulated, does not offer that. You cannot run an experiment to detect another universe. You cannot point a telescope and see a bubble. The evidence, if there is any, is indirect. Patterns in the cosmic microwave background, anomalies in the distribution of matter, subtle signatures that might, in principle, be left behind by collisions between bubbles in the distant past. Searches for those signatures are ongoing. So far, nothing definitive has been found. Despite the lack of direct evidence, the multiverse is taken seriously, not by everyone, but by a significant portion of the theoretical physics community. Why? Because it solves a problem that has been bothering physicists for decades: the fine-tuning problem. The laws of physics in our universe appear to be finely tuned for the existence of life. Change certain fundamental constants by even a small amount and the universe becomes uninhabitable. Make the strong nuclear force slightly weaker and atomic nuclei fall apart. Make it slightly stronger and hydrogen fuses too easily, and stars burn out before planets can form. Make the cosmological constant, the dark energy driving the accelerated expansion, much larger, and galaxies never form because space expands too fast for gravity to pull matter together. Make it much smaller, or negative, and the universe collapses before life has time to arise. The values of the constants we observe seem to sit in a narrow range that allows for complexity, chemistry, stars, planets, and eventually life. That looks suspicious. It looks like the universe was designed, or at least like the universe we happen to live in is absurdly lucky. The odds of randomly selecting a set of physical constants that permit life seem vanishingly small. Why do we live in a universe where the constants happen to have the right values? One answer is the anthropic principle. This is not a physical law, it is a selection effect. Observers can only exist in universes where the conditions permit observers to exist. If the multiverse is real, if there are countless bubble universes with different physical laws, then most of those universes are sterile. No stars, no planets. No chemistry, no life, no observers. We do not live in one of those universes because we cannot. We live in one of the rare bubbles where the constants happen to fall in the narrow range that allows complexity. Not because our universe is special, but because we are observers, and observers only arise in life-permitting universes. The apparent fine-tuning is not a cosmic coincidence. It is a selection effect. We're observing a biased sample. The universes we can observe are by definition the ones capable of producing observers. The Stanford report described the string theory landscape as the best theory physicists have come up with to explain this cosmic coincidence. That is high praise and also deeply uncomfortable. The multiverse does not explain why the landscape exists or why inflation produces bubbles. It just shifts the question. Instead of asking why our universe has the right constants, we ask why the multiverse generates universes with a range of constants, some of which happen to permit life. That is still a mystery, but it is a different mystery. And for some physicists, it is progress. The multiverse does not answer the ultimate question of why there is something rather than nothing. But it provides a framework in which our universe's apparent fine-tuning is not a miracle. It is statistics. Not everyone is convinced. Critics argue that the multiverse is not science because it is not testable. If you cannot observe other universes, if you cannot run experiments to confirm their existence, then the hypothesis is not falsifiable, and if it is not falsifiable, it is not science, it is philosophy. Or speculation. The argument is not entirely fair because science deals with unobservable entities all the time. Quarks were proposed long before they could be directly observed. Black holes were theoretical for decades before we had strong evidence they existed. The interior of a neutron star is unobservable. We cannot visit it. We cannot send probes inside. But we build models, make predictions, test those predictions against indirect observations. The same could be true for the multiverse. If the inflationary multiverse makes predictions about the cosmic microwave background or the distribution of physical constants, and those predictions can be tested, then it is science. The fact that we cannot directly observe other bubbles does not disqualify the idea. It just makes it harder to test. And there are other versions of the multiverse that have nothing to do with inflation or string theory. The many worlds interpretation of quantum mechanics is one. In standard quantum mechanics, when you measure a particle, it seems to collapse into a definite state. Before measurement, the particle exists in a superposition, a combination of multiple possible states. Measure it and you get one outcome. The wave function collapses. The many worlds interpretation argues that the collapse never happens. Instead, every possible outcome of a measurement occurs in a separate branch of reality. The universe splits. One branch contains the outcome where the particle was measured spin up. Another branch contains the outcome where it was measured spin down. Both branches are real. Both exist. You, the observer, only perceive one branch because you are part of that branch, but the other branch continues with a version of you that observed the other outcome. Every quantum measurement, every interaction where multiple outcomes are possible spawns new branches. The universe is constantly splitting into a vast, ever-growing tree of parallel realities. This is not fringe physics. The many worlds interpretation is one of the mainstream interpretations of quantum mechanics. It was proposed by Hugh Everett in the 1950s and has been developed and defended by serious physicists ever since. It solves the measurement problem, the question of why we observe definite outcomes when the math says particles should exist in superpositions. The answer is that we do not collapse the wave function. We become entangled with it. The superposition persists, but we only experience one branch. The interpretation is controversial. It sounds absurd, an infinite number of parallel universes splitting off every time a particle interacts. But the math works, and it does not require any modification to the standard equations of quantum mechanics. You just take the equations seriously and follow them to their logical conclusion. The result is the many worlds multiverse, a branching tree of realities where every possible outcome happens somewhere. Some modern discussions extend the many worlds idea beyond quantum measurements to include different laws of physics in different branches. That pushes the interpretation into more speculative territory, blending it with the inflationary multiverse or the string landscape. But even in its conservative form, the many worlds interpretation suggests that what we call reality is just one thread in a much larger tapestry. Every decision you have ever made, every coin flip, every quantum event has spawned branches where different outcomes occurred. There are versions of you, in other branches, who made different choices, experienced different lives, ended up in different places. You cannot visit those branches. You cannot communicate with those other versions of yourself. The branches are causally isolated. But according to the interpretation, they are as real as the branch you're experiencing right now. And then there is the simulation hypothesis. This is not a scientific theory in the usual sense. It is a philosophical argument, but one that has gained traction in recent years, partly because of advances in computing, and partly because it is hard to definitively rule out. The basic idea is simple. If it is possible to create a simulation of conscious beings, a virtual reality detailed enough that the simulated beings cannot tell they are in a simulation, then it is likely that such simulations have been created. And if simulations exist, there are probably far more simulated realities than base realities. Most observers would therefore be living in simulations, not in the original unsimulated universe. So statistically, we are probably in a simulation. The argument was formalized by philosopher Nick Bostrom in the early 2000s, though variations of the idea have been around much longer. Bostrom outlined three possibilities. Either civilizations never reach a level of technology where they can create detailed simulations of conscious beings, or they reach that level but choose not to run such simulations. Or they do create simulations, in which case simulated realities vastly outnumber base reality, and we are probably in one. The argument is not airtight. It makes assumptions about computational capacity, the nature of consciousness, and the motivations of advanced civilizations. But it's hard to dismiss outright. Modern philosophical treatments argue that it is possible we inhabit a simulation, even if the hypothesis remains speculative and not empirically established. The simulation hypothesis is not testable in any straightforward way. If the simulation is sufficiently detailed, there is no experiment you can run that would reveal you are inside it. Any anomaly you detect could be explained as a bug, or as intended behavior, or as something you misunderstood. The hypothesis is unfalsifiable, which puts it in the same category as the multiverse for critics who demand testability. And yet the idea is compelling because it connects to real questions about the nature of reality and the limits of our knowledge. If we are in a simulation, what is outside the simulation? Who is running it? What are their purposes? The questions spiral outward, becoming less and less answerable. The simulation hypothesis does not explain the universe. It just moves the explanation one level up. you still have to explain where the simulators came from, what their universe is like, whether they are themselves in a simulation. It is turtles all the way down, or all the way up, depending on how you look at it. The common thread running through all these ideas, the inflationary multiverse, the string landscape, the many worlds interpretation, the simulation hypothesis, is that they all suggest reality is larger, stranger, and more layered than we directly experience. The universe we see, the 93 billion light-year bubble we can observe, might be a tiny fraction of what exists. One bubble in an infinite foam, one branch in an infinite tree, one simulation in a stack of nested realities. These ideas challenge the notion that what we see is all there is. They force us to confront the possibility that most of reality is hidden from us, not because we lack the instruments to observe it, but because it is fundamentally beyond the reach of observation. That brings us to the deepest question of all. Why does the universe exist? Why is there something rather than nothing? Physics can tell us how the universe works. It can describe the forces, the particles, the laws that govern interactions. It can trace the history of the cosmos back to the first fractions of a second after the Big Bang. But it cannot tell us why there was a Big Bang in the first place. Why did the universe begin? Why does it follow the laws it does? Why are there laws at all? These are not questions physics is equipped to answer. They sit at the boundary between science and philosophy, and they remain open. The search for a theory of everything, a single unified framework that would explain all the forces and particles in a coherent way, is ongoing. String theory is one candidate. Loop quantum gravity is another. There are others. But no confirmed theory of everything exists yet. And even if we found one, even if we discovered a single set of equations that perfectly described all of reality, we would still face the question of why those equations apply, why that particular set of laws and not some other set. The theory of everything would explain how the universe works. It would not explain why it exists. That gap between description and explanation is where physics ends and philosophy begins, and it is a gap that might never be closed. The multiverse idea changes the way we think about our place in the world. That is a quote from a review of multiverse theories. It is true. If the multiverse is real, we are not living in the universe. We are living in a universe, one of many, possibly one of infinitely many. Our physical laws are local, not universal. The constants we measure, the forces we observe, the structures we see, all of it is specific to our bubble, our branch, our slice of a much larger reality. That is humbling. It shrinks our significance. We're not at the center of anything, not the center of the solar system, not the center of the galaxy, not the center of the universe. And now, possibly, not even living in a unique or special universe. Just one observer in one bubble in an infinite multiverse, asking questions about a reality vastly larger than we can ever hope to see. And yet, here we are, asking those questions, building telescopes, running experiments, mapping the cosmic web, measuring the expansion of space, searching for dark matter, trying to understand dark energy. The universe, or the multiverse, or whatever this is, has given rise to structures complex enough to ask questions about their own existence. Stars formed, planets coalesced, chemistry became biology, biology became awareness, awareness became science. And now we're using the laws of physics to probe the origins of those laws, using the universe to study the universe, using our brains built from stardust to map the cosmos that made us. That is extraordinary. It does not require a multiverse to be meaningful. It does not require fine-tuning to be worth celebrating. The fact that we are here, capable of asking these questions, capable of building models and testing them and refining them, is remarkable regardless of how many other universes exist or do not exist. The observable universe is 93 billion light-years across. Beyond that, more universe, possibly infinite, possibly containing structures we will never see. And beyond that, possibly a multiverse. Bubbles and branches and layers of reality stacked in ways we're only beginning to imagine. We do not know which of these ideas is correct. We might never know. The horizon of the observable universe is a hard limit. The particle horizon is not something we can push past by building a better telescope. It is set by the speed of light and the age of the universe. We can only see so far. Beyond that, we are left with models, with math, with speculation grounded in the physics we understand but extending into realms we cannot directly test. The controversy around the multiverse is real. It is difficult or impossible to test directly, so some physicists question whether it is scientific in the usual experimental sense. That is a fair criticism. Science is built on testability. Hypotheses should make predictions that can be confirmed or refuted. The multiverse, in many of its forms, does not offer that. But it is worth remembering that the boundary between testable and untestable is not always sharp. Ideas that seem untestable today might become testable tomorrow with new technology or new theoretical insights. And some questions are worth asking even if we cannot answer them yet. The multiverse is one of those questions. It is speculative, it is controversial, it might be wrong, but it is serious. It emerges naturally from our best theories of inflation and quantum mechanics. It addresses real problems, like the fine-tuning of physical constants and the measurement problem in quantum theory. It deserves to be taken seriously even if we cannot yet confirm it. The universe has surprised us before. Every time we thought we understood the big picture, new observations forced us to revise. The Earth is not the centre of the solar system. The solar system is not the centre of the galaxy. The Milky Way is not the entire universe. The universe is not static. It is expanding. It is accelerating. It is dominated by dark matter and dark energy, substances we cannot see and do not understand. 2 trillion galaxies, hundreds of billions of planets, a cosmic web stretching across billions of light years, and all of it, the entire observable universe, might be just one bubble in a much larger multiverse. That pattern of discovering that reality is larger and stranger than we thought has repeated throughout history. Why should it stop now? We are standing on the edge of the known, looking out into the dark. We have mapped the observable universe. We have traced its history back to the first moments after the Big Bang. We have found planets around other stars. We have detected gravitational waves from colliding black holes. We have imaged the event horizon of a supermassive black hole. We have measured the accelerating expansion of space. We have built the Large Hadron Collider and confirmed the Higgs boson. We have done extraordinary things, but the biggest questions remain unanswered. What is dark matter? What is dark energy? Is there a multiverse? Is there a theory of everything? Why does the universe exist? We do not know. Not yet. Maybe not ever. But we are looking. And every answer we find opens new questions, pushes the frontier a little farther out, reveals another layer of the cosmos we did not know was there. This is where the story ends, not because we have run out of universe to explore, but because we have reached the limits of what we can currently observe and understand. Beyond the cosmic horizon, beyond the inflationary multiverse, beyond the branching worlds of quantum mechanics, beyond the possibility that we are simulations in someone else's computer, there might be something else, something we have not imagined yet, something we do not have the concepts or the language to describe. Reality is under no obligation to make sense to us. It is under no obligation to be knowable. We are one species on one planet orbiting one star in one galaxy, in one universe, or one bubble, or one branch, or one simulation. We are small. The cosmos is vast, and most of it, by any measure, is hidden from us. Dark matter, dark energy, unobservable regions beyond our particle horizon. Possible other universes we can never visit. We live in a universe where 95% of the content is invisible, and most of the space is forever out of reach. That should be humbling. It should remind us how little we know, how much remains to be discovered, how far we still have to go. But it should also be inspiring. Because despite all of that, despite the darkness and the distance and the limits of observation, we are here, asking questions, building instruments, testing theories, pushing the boundaries of knowledge outward, one observation at a time. The universe is not obligated to reveal its secrets, but we are going to keep looking anyway. Because that is what we do. That is what makes us human. The capacity to wonder. The drive to explore. The refusal to accept that the horizon is the end of the story. It is not the end. It is just the edge of what we can see. And beyond that edge, there is more. Always more. Waiting to be discovered. You have just travelled 93 billion light years. You have crossed the solar system, passed through the lives and deaths of stars, fallen into black holes, mapped galaxies, traced the cosmic web, and stared into the invisible architecture holding everything together. You have seen a universe that is mostly dark, mostly hidden, mostly unknown. 95% of it refuses to show itself. And yet here we are, made of stardust, asking questions about the very fabric of reality, using atoms forged in ancient supernovae to build telescopes that peer back toward the beginning of time itself. The universe does not owe us answers. It does not owe us meaning. It simply is. A vast, expanding, accelerating structure governed by laws we're still learning, filled with objects we're still discovering, shaped by forces we cannot see. We live in a cosmos where most of the matter is invisible, where most of the energy is unexplained, where most of the space will forever remain beyond our reach. And still we look. Still we measure. Still we ask why. There may be other universes. There may be infinite branches, infinite bubbles, infinite versions of this moment playing out in ways we will never witness. Or this might be all there is. One universe, one chance, one fragile arrangement of matter and energy that happened to produce eyes capable of looking outward and minds capable of understanding what they see. Either way, the fact that we are here, capable of tracing our origins back to the Big Bang, capable of mapping the structure of space-time itself, capable of asking whether we are alone in a multiverse or alone in a single cosmos, that fact alone is worth something. Maybe everything. The horizon is not the end, it is just the edge of what we can see. And beyond that edge, there is more, always more, waiting.